When you look up at the night sky, you see what seems like a scattered handful of stars, twinkling points of light that feel familiar and small. For thousands of years, humans believed that everything they could see belonged to one single structure, our own galaxy. The universe felt complete, contained, knowable. But what we thought was everything turned out to be almost nothing at all. Scientists have discovered that our galaxy is just one among countless others, scattered across distances so vast that light itself takes billions of years to travel between them. The universe isn't the quiet, orderly place we once imagined. It's overflowing with structures we're only beginning to understand, filled with more galaxies than there are grains of sand on every beach on Earth. Tonight we'll explore how we came to discover this abundance, how we count what seems uncountable, and what it means to live inside something so impossibly vast. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Above our heads, past the quiet darkness that settles over our world each night, there exists something almost impossible to grasp. The observable universe holds at least 2 trillion galaxies, each one a collection of hundreds of billions of stars. When we try to understand this number, our minds naturally stumble because we weren't built to think in such vast scales. Ancient humans looked up at the night sky and saw the same points of light we see today. They created stories about those lights, mapping out constellations and using stars to navigate across oceans and deserts. For thousands of years, every culture on Earth believed that all the stars belonged to one great structure. They saw the Milky Way stretching across the sky like a river of light, and assumed that was everything. The rest of space seemed empty, just darkness between the stars. This understanding persisted for millennia, because the human eye can only see so much. Even the brightest minds of their time couldn't imagine that those faint, fuzzy patches of light scattered across the sky were actually entire galaxies, each containing more stars than there are grains of sand on all the beaches of Earth. The shift in our understanding happened slowly, gently, through the work of curious people who sat in the cold night air, peering through simple telescopes. They noticed cloudy patches that didn't behave like stars. These nebulae, as they called them, refused to resolve into single points of light, no matter how much they magnified them. Some were indeed clouds of gas within our own galaxy, glowing with the light of nearby stars, but others were something entirely different. These early astronomers were looking at entire galaxies, island universes so distant that their light had been traveling for millions of years to reach us. Think about that for a moment. When you look up at the night sky tonight, you're not just looking through space, you're looking backward through time. The light from the moon left its surface just over a second ago. Light from the nearest star took 4 years to reach your eyes. And the light from some galaxies began its journey billions of years before our planet even existed. This means that when we count galaxies, we're not really counting what exists now, but what existed long ago. The universe is so vast that distance and time become the same thing. Every galaxy we see is a fossil of light, carrying information about the universe as it once was. Modern space telescopes have revolutionized our ability to peer into deep space. They orbit above Earth's atmosphere, avoiding the distortion and haze that limits ground-based telescopes. These instruments have revealed galaxies in every direction we look, scattered through space, like seeds in an infinite garden. When astronomers want to count galaxies, they use a clever technique. They point their most sensitive instruments at a tiny patch of sky, sometimes no larger than a grain of sand held at arm's length. Then they examine that small area in extraordinary detail, cataloguing every faint smudge of light they can detect. What they find is remarkable. Even in these tiny patches, thousands of galaxies appear, each one containing billions of stars. The astronomers then multiply this number across the entire sphere of the sky. The results suggest there are at least 2 trillion galaxies in the part of the universe we can observe. But here's where it gets philosophically interesting. We can only see as far as light has had time to travel since the universe began, about 13.8 billion years ago. Beyond that lies a region we simply cannot see, perhaps filled with countless more galaxies that remain forever beyond our reach. Each galaxy is its own unique world. Some are massive spirals like our Milky Way, rotating slowly with elegant arms that sweep through space over millions of years. These spiral arms aren't solid structures, but density waves that move through the galaxy like ripples in a pond. Stars form along these arms, creating the bright patterns we see from vast distances. Other galaxies are elliptical, appearing smooth and oval-shaped. These tend to be older systems, filled with ancient red stars that have been burning for billions of years. They've used up most of their gas for making new stars, so they're like cosmic retirement communities, peaceful and stable. Many galaxies are small and irregular, chaotic collections of gas and young blue stars. These systems often look like cosmic fireworks, with bright regions where new stars are being born at rapid rates. Some are interacting with nearby galaxies, their shapes distorted by gravitational forces that stretch them into long streams and tails. Between all these galaxies lie immense voids, regions so empty that if you were somehow transported there, the nearest galaxy might be hundreds of millions of light years away. These voids contain very little matter, just occasional wisps of gas, and perhaps some mysterious dark matter that we can't directly detect. The space between galaxies isn't completely empty though. A thin soup of particles drifts through these regions, along with radiation left over from the Big Bang itself. This cosmic microwave background radiation fills all of space, a faint afterglow from when the universe was much younger and hotter. Dark matter plays a crucial role in how galaxies form and behave. This invisible substance makes up most of the matter in the universe, yet it doesn't emit or absorb light. We only know it exists because of its gravitational effects on visible matter. Dark matter provides the scaffolding around which galaxies form, creating invisible halos that extend far beyond the visible stars. Galaxy formation began relatively early in cosmic history, when the universe was only a few 100 million years old. Small clumps of dark matter gradually attracted ordinary matter, which condensed into the first stars and galaxies. These early systems were much smaller and more chaotic than the grand spirals we see today. Over billions of years, galaxies have grown through mergers and accretion. Small galaxies combine to form larger ones, while streams of gas from intergalactic space provide raw material for new star formation. Our own Milky Way is currently in the process of absorbing several smaller satellite galaxies, and in about 4 billion years, it will merge with the nearby Andromeda galaxy. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old. These ancient systems look very different from modern galaxies, often appearing more compact and irregular. They represent snapshots of cosmic youth, showing us what galaxy formation looked like in the early universe. Some galaxies harbor supermassive black holes at their centers, objects millions or billions of times more massive than our Sun. These black holes can dramatically influence their host galaxies, either triggering intense bursts of star formation or shutting it down entirely by heating up the surrounding gas. The most active of these systems are called quasars, where material falling into the central black hole creates brilliant beacons of light that can outshine entire galaxies. Quasars were much more common in the early universe, suggesting that galaxy formation was a more violent process back then. When we consider the total number of galaxies, we're really trying to count something that's constantly changing. New galaxies form through mergers, while others fade as they exhaust their gas supplies. The expansion of the universe carries distant galaxies ever further away, eventually moving them beyond our ability to observe them. This ongoing cosmic evolution means that any count of galaxies is really a snapshot of a particular moment in time. The universe we see today represents about 13.8 billion years of cosmic history, but that history is still being written. Stars are still forming, galaxies are still merging, and new structures are still emerging from the cosmic web. The philosophical implications of these numbers are profound. If there are truly 2 trillion galaxies in the observable universe alone, and each contains hundreds of billions of stars, then the total number of stars becomes almost meaningless. We're looking at a number so large that it exceeds the number of grains of sand on all the beaches and deserts of Earth. This vastness puts our own existence into a peculiar perspective. We live on one planet, orbiting one star, in one galaxy among trillions. Yet somehow, through the power of curiosity and careful observation, we've managed to map the structure of the entire observable universe. It's a remarkable achievement for a species that only learned to fly a little over a century ago. The act of counting galaxies connects us to something fundamental about consciousness itself. We are, as far as we know, arrangements of matter that have become aware of themselves and curious about their surroundings. In trying to understand the cosmos, we're really exploring the capacity of organized matter to comprehend its own origins and context. Perhaps the most beautiful aspect of galaxy counting is its essential incompleteness. No matter how sensitive our instruments become, there will always be fainter, more distant galaxies just beyond our reach. The universe keeps some of its secrets, maintaining an eternal frontier for curiosity to explore. This unknowability isn't a limitation, it's a gift. It means that wonder never has to end, that there's always more to discover, always another question to ask. The night sky remains an invitation to dream, to imagine, and to feel connected to something vast and mysterious. The universe operates like a vast recycling program that's been running for over 13 billion years. Every element in your body, except for hydrogen, was forged inside the nuclear furnaces of ancient stars. The calcium that makes your teeth strong, the iron that carries oxygen through your bloodstream, the carbon that forms the backbone of every protein, all of these came from stellar explosions that happened long before Earth even existed. When massive stars reach the end of their lives, they don't simply fade away quietly. They explode in what astronomers call supernovae, blasting their enriched contents across space at speeds of thousands of kilometers per second. These cosmic detonations scatter heavy elements throughout galaxies, seeding future generations of stars and planets with the raw materials needed for complexity. Our Milky Way galaxy contains somewhere between 200 and 400 billion stars. Each one represents a nuclear reactor that's been burning for millions or billions of years, converting simple hydrogen into increasingly complex elements through a process called stellar nucleosynthesis. The bigger the star, the more elements it can create before it dies. But here's where the numbers become almost incomprehensible. The Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Each of those distant island universes contains its own population of stars, its own history of stellar births and deaths, its own contribution to the cosmic recycling program. The Hubble Space Telescope has peered into what astronomers call the deep field, regions of sky that appear completely empty to the naked eye. When Hubble stares at these patches of apparent nothingness for days at a time, collecting every photon of light, thousands of galaxies emerge from the darkness. Some of them are so distant that we're seeing them as they appeared when the universe was less than 1 billion years old. Think about what this means for a moment. Light travels at 300,000 kilometers per second. Yet some of the galaxies we observe are so far away that their light has been traveling toward us for over 13 billion years. We're literally looking back in time, watching the universe's childhood unfold in slow motion. The Andromeda Galaxy, our nearest large galactic neighbor, sits about 2.5 million light-years away. On a clear, dark night, you can actually see it with your naked eye as a faint smudge in the constellation Andromeda. That fuzzy patch of light contains roughly 1 trillion stars, each potentially hosting its own family of planets. Astronomers have discovered that galaxies aren't scattered randomly through space. They cluster together in vast structures called galaxy clusters, which themselves are connected by filaments of dark matter stretching across hundreds of millions of light-years. Between these cosmic highways lie enormous voids, regions of space so empty they contain almost nothing at all. The process of galaxy formation began shortly after the Big Bang, when tiny fluctuations in the density of matter started to grow under the influence of gravity. Over millions of years, these small variations became the seeds that eventually grew into the first stars and galaxies. The universe was a much different place back then, smaller, hotter, and filled with the afterglow of creation. Dark matter plays a crucial role in holding galaxies together. This invisible substance, which makes up about 27% of the universe, provides the gravitational scaffolding that prevents galaxies from flying apart as they rotate. Without dark matter, the stars in the outer regions of galaxies would be moving too fast to remain gravitationally bound to their galactic homes. Every galaxy has its own unique personality shaped by its history of mergers, star formation, and interactions with neighbors. Some galaxies are actively forming new stars at a furious pace, lighting up with the blue glow of young, hot, stellar nurseries. Others have exhausted their gas supplies and shine with the reddish light of older, more mature stellar populations. The supermassive black holes that lurk at the centers of most galaxies can influence star formation across their entire galactic domains. When these cosmic monsters feed on surrounding material, they can generate powerful jets of energy that either trigger new waves of starbirth or shut down star formation entirely by heating and dispersing the galaxy's gas supply. Galaxy collisions, despite sounding catastrophic, are actually relatively gentle affairs that unfold over hundreds of millions of years. When two galaxies merge, their individual stars rarely collide directly because of the vast distances between them. Instead, gravitational forces reshape both galaxies, often triggering spectacular bursts of new star formation as gas clouds compress and collapse. Our own Milky Way is currently on a collision course with Andromeda, though the merger won't occur for another 4.5 billion years. When it happens, the night sky will be dramatically different, filled with the combined light of two galaxies' worth of stars. Some astronomers have already coined a name for the resulting galaxy, Milkomeda. The concept of cosmic humility emerges naturally when you contemplate these scales. We exist on a planet that orbits an ordinary star in the suburbs of an unremarkable galaxy, one among trillions scattered throughout an expanding universe. Yet this perspective doesn't diminish our significance. It transforms our understanding of what significance means. Perhaps the most profound realization is that the universe has evolved in such a way that it can now contemplate itself through conscious observers like us. The atoms that form our brains were assembled in stellar cores, injected into space, incorporated into planetary systems, and eventually organized into patterns complex enough to ponder their own origins. The light from distant galaxies carries information about conditions that existed billions of years ago, allowing us to piece together the story of cosmic evolution. Each photon that enters our telescopes has traveled across unimaginable distances, surviving the expansion of space itself to deliver messages from the ancient universe. Modern estimates suggest there might be as many galaxies in the observable universe as there are stars in our own Milky Way. That's a number so large, it challenges our ability to even conceptualize it meaningfully. 2 trillion galaxies, each containing billions or trillions of stars, each potentially hosting planets, each planet representing countless opportunities for complexity to emerge. The realization that we are literally made of star stuff isn't just poetic metaphor, it's scientific fact. The nuclear processes that created the elements in our bodies occurred at temperatures of hundreds of millions of degrees, under pressures that would instantly vaporize any known material. Yet, here we are, walking around as living monuments to stellar alchemy. When we gaze up at the night sky, we're not separate observers looking at a distant show. We're participants in an ongoing cosmic story, temporary arrangements of stardust that have somehow learned to wonder about their place in the larger narrative. The universe isn't something we study from the outside. It's something we experience from within, as conscious expressions of its own creative potential. The stars have always been there, waiting quietly above us while we go about our daily business. During daylight hours, they're completely invisible, hidden by the brightness of our own sun. It's only when darkness falls that we can see what's been overhead all along. This simple fact reveals something profound about observation itself, how the act of looking requires the right conditions, the right moment, the right kind of darkness. Our galaxy, the Milky Way, appears as a faint band of light stretching across the night sky. What we're seeing isn't actually fog or mist. even though it looks like it. Instead, we're looking at billions of individual stars, so distant that they blur together into a soft ribbon of light. Each tiny point is actually a massive sun, burning with nuclear fire, perhaps surrounded by its own planets. The distance to these stars is almost impossible to comprehend. Light travels at roughly 186,000 miles per second, faster than anything else in the universe. Even at this incredible speed, light from some stars takes years, decades, even centuries to reach us. When you look up at the night sky, you're literally seeing into the past. The light hitting your eyes left those stars long before you were born. Throughout human history, different cultures have given the Milky Way different names. Some called it the Path of Souls. Others saw it as spilled milk from the gods. The ancient Greeks thought it was the road that led to Zeus's palace. These varied interpretations show how humans have always felt compelled to find meaning in the patterns above them, to create stories that make sense of the vastness. Before we had telescopes, the naked eye could only see about 3,000 stars on a clear night. That seems like a lot, but it's actually just a tiny fraction of what's really out there. Our galaxy alone contains somewhere between 100 and 400 billion stars. The entire observable universe might hold more stars than there are grains of sand on every beach on Earth. The constellations we recognize today won't look the same forever. Stars are constantly moving through space, orbiting the center of our galaxy at tremendous speeds. The Big Dipper, Orion, the Southern Cross, all these familiar patterns are temporary arrangements that will slowly shift and change over thousands of years. Future humans will see completely different shapes in the sky. Most people living in cities today have never seen the full night sky. Light pollution from streetlights, buildings, and electronic displays washes out all but the brightest stars. We've traded our view of the cosmos for the convenience of artificial lighting. In some ways, this represents a fundamental disconnection from something that guided and inspired our ancestors for millennia. But travel to a truly dark location, far from city lights, and the sky transforms into something extraordinary. The Milky Way becomes bright enough to cast shadows. You can see subtle colors, golden hues near the galactic center, blues and silvers along the edges. On exceptionally clear nights, you might even spot the Magellan Clouds, two small galaxies that orbit our own. The space between stars isn't actually empty, even though it appears that way. It's filled with incredibly thin gases, cosmic dust, magnetic fields, and various forms of radiation. There's also something called the cosmic microwave background, which is leftover light from the Big Bang itself. This faint glow permeates the entire universe, a kind of fossil radiation from when the cosmos was much younger and hotter. Every photon of starlight that enters your eye has completed an incredible journey. It began in the nuclear furnace at a star's core, where hydrogen atoms fuse together to create helium, releasing tremendous amounts of energy in the process. That energy slowly works its way to the star's surface, then travels across the emptiness of space for years or centuries before finally reaching Earth. Our galaxy is roughly 100,000 light-years across. That means light, traveling at its maximum possible speed, takes 100,000 years to cross from one edge to the other. To put this in perspective, modern humans have only existed for about 300,000 years. The light we see from the far side of our own galaxy began its journey before our species developed agriculture, before we built cities, before we learned to write. And yet, vast as our galaxy is, it's just one among billions in the observable universe. If you could somehow step outside and look back at the Milky Way, you'd see a spiral structure with curved arms of stars, gas, and dust. Our solar system sits about halfway out from the center, in a relatively quiet neighborhood called the Orion Arm. The nearest major galaxy to us is Andromeda, visible to the naked eye as a faint smudge in the constellation of the same name. Andromeda contains roughly 1 trillion stars and is currently moving toward us. In about 4.5 billion years, it will collide with our galaxy, though collision isn't quite the right word, since the distances between stars are so vast that very few will actually crash into each other. Beyond Andromeda lie countless other galaxies, each containing billions or trillions of stars. Some are spiral-shaped like ours. Others are elliptical or irregular. They cluster together in groups and superclusters, forming a cosmic web of matter separated by enormous voids of mostly empty space. The largest structures in the universe are these galactic filaments, chains of galaxies, stretching across hundreds of millions of light-years. When astronomers look at very distant galaxies, they're seeing them as they were billions of years ago, when the universe was much younger. Some of the most distant objects we can detect appear as they were when the universe was less than 1 billion years old. These ancient galaxies look different from modern ones, smaller and more chaotic. Still, in the process of forming the first generation of stars, the night sky connects us to this vast cosmic story in a direct, immediate way. Every time you look up, you're participating in the same act of observation that humans have engaged in for thousands of generations. You're seeing the same stars that guided ancient navigators, inspired poets, and sparked the curiosity that eventually led to modern astronomy and space exploration. Light from the most distant galaxies carries stories that stretch back through cosmic time, whispering secrets about what existed when the universe was young and strange. These faint signals have traveled for billions of years, crossing unimaginable distances just to reach our eyes tonight. When we catch that ancient light, we're not just observing distant objects, we're actually looking backward through time itself. Scientists decode these cosmic messages to piece together the universe's biography, tracing how everything expanded from an incredibly hot, dense beginning into the sprawling network of galaxies we see scattered across space today. Each photon becomes a tiny messenger, carrying information about temperature, composition, and movement from eras when the cosmos looked completely different than it does now. There's something deeply moving about the act of looking up at stars, even when we use sophisticated instruments instead of just our naked eyes. The technology may be complex, the data stream's enormous, but the fundamental urge remains exactly the same as what drove our ancestors to give names to patterns in the sky. We're still asking the same questions, still trying to understand our place in all of this vastness. Astronomy becomes a kind of cosmic archaeology, digging through layers of light to uncover the past. Every observation connects us to that ancient lineage of curiosity, that persistent human need to know what lies beyond our immediate world. We might use digital sensors now, instead of relying purely on vision, but the desire hasn't changed at all. We want to understand where we are, and whether we might share this space with others. For most of human history, people believed all the stars belonged to a single great sphere that surrounded Earth. The revolutionary idea that those points of light might actually be suns like ours, scattered throughout a vast emptiness, took centuries to gain acceptance. Even harder to grasp was the possibility that those distant suns might belong to entirely separate galaxies, complete systems existing far beyond our own Milky Way. You can understand why this was so difficult to accept. When you live under the same familiar sky night after night, it feels complete, like everything that exists. It requires a special kind of imagination to believe that those faint, barely visible smudges at the edge of your vision are actually entire universes in their own right, spinning and evolving according to their own cosmic schedules. But that's exactly what they are. Every dim glow represents an island of creation, containing billions of stars, planets, and possibilities we can barely comprehend. The night above us exists in this strange state of being, both constant and constantly changing. Constellations shift slowly as Earth wobbles on its axis over thousands of years. Stars are born from clouds of gas and dust, live their lives, and die, though we rarely witness these events within a human lifetime. Some stars flare up dramatically before fading away. Others simply dim quietly over millions of years, and new ones emerge from stellar nurseries hidden throughout the galaxy. The Milky Way itself moves through space, pulled gently by the gravitational influence of neighboring galaxies. Someday, far in the future, our galaxy will collide with Andromeda, another massive spiral that's currently approaching us at hundreds of kilometers per second. When that cosmic collision occurs, the night sky will transform completely. The stars of both galaxies will mingle and dance, creating something entirely new, brighter, larger, and utterly different from what we see today. But that event lies billions of years in the future. For now, the two galaxies drift closer, in cosmic silence, their light crossing the void like distant lighthouses, glimpsing each other across a dark ocean. There's something quietly comforting about knowing that the stars you see tonight participate in this ever-changing universe. You don't need to understand every detail to feel connected to its rhythm. The galaxies, the individual stars, the seemingly empty space between them, they all move in patterns too large for human timescales to comprehend easily. Yet somehow, their slow, majestic motion gives meaning to our brief moments of existence. When you see a shooting star streak across the sky, you're watching a tiny grain of cosmic dust burn up as it hits our atmosphere. When you look at the moon, you're seeing sunlight reflected off rock that has been orbiting Earth for more than 4 billion years. Every glance upward becomes an encounter with deep history, a reminder that we're part of a story much older than any civilization or even any species on Earth. On particularly clear nights, when the moon is dark and the air is still, you can sometimes see the faint glow of distant galaxy clusters, regions where thousands of galaxies gather together, held in gravitational embrace. These clusters appear as subtle patches of light, barely visible to the naked eye. Yet each one could contain more galaxies than you could count in a lifetime. They represent the cities of the cosmos, enormous gatherings of matter organized by invisible scaffolds of dark matter that we're only beginning to understand. Between these clusters lie cosmic voids, vast regions that are almost entirely empty of matter. The pattern formed by clusters and voids creates what astronomers call the cosmic web, an immense structure that spans the observable universe. It's nearly impossible to picture accurately, but if you could somehow step outside the universe and look back, you would see galaxies arranged in long filaments and dense knots, like veins of light stretching through an ocean of darkness. All of this cosmic architecture begins with what you can see above you on any quiet night. Ancient travelers used stars as navigation guides, treating the sky as their map for crossing oceans and continents. Today we still use it as a guide, though for very different kinds of journeys. Instead of crossing physical distances, we cross time itself. Instead of measuring miles, we measure in light years and cosmic epochs. Each new observation takes us a little further toward understanding, but the destination keeps moving away from us, like a horizon that recedes as you walk toward it. That's part of what makes this so wonderful. The night sky doesn't just show us where we are in space, it constantly reminds us that there's always more to discover, more to learn, more to wonder about. Every answer we find opens up new layers of mystery, new questions we hadn't even thought to ask before. Imagine the first moment when someone realized that certain faint, fuzzy patches weren't stars at all, but entire galaxies lying far beyond our own. That single realization changed the human understanding of existence forever. It meant that our entire galaxy, with its hundreds of billions of stars that people once thought represented the complete universe, was actually just one among countless others. It meant that the night sky wasn't a nearby dome decorated with lights, but rather a window looking out into an almost infinite expanse, filled with unimaginable wonders. Most importantly, it meant that the universe doesn't center on us, but that we're participants in something far greater than ourselves, something shared by everything that exists anywhere. This realization is humbling, certainly, but it's also profoundly comforting, because it means that the darkness above us isn't empty space at all. It's filled with company, with countless other worlds and possibilities. If you were to close your eyes right now and picture the night sky, you might visualize stars as tiny points scattered across blackness. But in reality, what you're imagining represents only a tiny fraction of what actually exists out there. Most galaxies remain completely invisible to human eyes, because their light is too faint or their distance too enormous to perceive directly. Yet they're definitely there, existing in numbers beyond our ability to count accurately. Some galaxies are so distant that their light has been stretched by the ongoing expansion of the universe into wavelengths we can't see without special instruments. Others hide behind cosmic dust clouds, shining brightly in infrared rather than visible light. As our telescopes and detection methods improve, We keep discovering more galaxies so faint that even our most powerful instruments barely register them as dim smudges against the cosmic background. Each new discovery pushes the boundary of the known universe a little further outward, revealing that reality is even more vast and populated than we previously imagined. The night above us serves as more than just a beautiful view. It provides evidence about the nature of existence itself. It tells us where we came from and what we're part of in the grand scheme of things. Every particle of light that reaches us carries detailed information about the state of the universe when it began its journey toward Earth. By carefully analyzing that light, studying its color, brightness, and spectral properties, astronomers can determine the age, distance, chemical composition, and motion of distant galaxies. In a very real sense, the sky whispers its secrets to us constantly through these signals. We're simply getting better at learning how to listen and interpret what we hear. The more we learn through these cosmic conversations, the more we realize that the universe isn't a static, unchanging place, but something alive with motion, energy, and constant transformation. The night sky above us represents the universe's most honest and direct expression of this dynamic reality. Looking up at the night sky has always done something peculiar to the human mind. There's this automatic quieting that happens when you tilt your head back and stare into that endless darkness. Your breathing slows down, your thoughts seem to drift, and suddenly all those daily worries feel smaller somehow. This isn't just because you're standing in a peaceful place. Something deeper is going on here, something that connects us to the very core of what we are. Our brains didn't develop in cities or buildings or even caves, really. They evolved under this exact same sky, watching these same patterns of light and dark cycle through seasons and years. The rhythm of day and night, the way stars wheel overhead, the phases of the moon, all of this became part of our internal wiring over millions of years. So when you feel that sense of calm, looking upward, you're actually reconnecting with something ancient in your biology. Every atom in your body was forged inside a star, billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it came from nuclear furnaces burning in space, long before Earth even existed. When those stars died in spectacular explosions, they scattered these elements into space, where they eventually clumped together to form planets, and eventually, life. In a very real sense, you're made of starlight. Looking back at your cosmic family, the night sky you see is actually just the inside view of our home galaxy. Every single point of light, visible to your naked eye, belongs to the Milky Way, a vast spiral of perhaps 400 billion stars. We're sitting about 2/3 of the way out from the center, in what astronomers call a quiet, suburban neighborhood of the galaxy. The dense band of light that stretches across dark skies, that's us looking through the thick disk of our galactic home from the inside. For most of human history, people saw the night sky as a collection of individual stars, each one a separate point of light hanging in the darkness. They connected these dots into patterns, drawing imaginary lines between stars to create pictures. Hunters, animals, mythical heroes. These constellations were humanity's first attempt to organize the chaos of the cosmos into something manageable, something that told stories. The ancient Greeks called that faint river of light across the sky the Milky Way, imagining it as milk spilled by a goddess. The Romans thought of it as a road for their gods to travel. Chinese astronomers saw it as a silver river flowing through heaven. The Maya believed it was the backbone that held up the sky itself. Each culture tried to make sense of this mysterious glow in their own way, creating beautiful myths to explain something beyond their understanding. When Galileo pointed his telescope at the Milky Way in 1609, he made a discovery that shattered these ancient stories. That smooth band of light suddenly broke apart into countless tiny stars, far too numerous and distant to see individually with the naked eye. What looked like fog or milk or divine pathways was actually an ocean of suns, each potentially warming its own family of planets. This moment marked one of the first great expansions of human perspective. The universe wasn't a simple dome with light stuck to it. It was deep, layered, filled with structure we could barely begin to imagine. The sky that had seemed flat and close was revealed to have dimensions stretching far beyond anything humans had ever conceived. Brother and sister astronomers William and Caroline Herschel spent decades in the late 1700s mapping stars systematically. They measured brightness, noted colors, estimated distances, slowly building the first scientific picture of our galaxy's shape. William imagined the Milky Way as a great flat disk of stars with our sun somewhere near the middle. He was wrong about our position. We're actually off to one side, but his intuition about the overall structure was remarkably accurate for its time. The word galaxy itself comes from the Greek term for milky, connecting our modern scientific understanding back to those ancient mythological names. In a strange way, the word was waiting centuries for science to catch up and give it proper meaning. Once astronomers realized our Milky Way was a massive island of stars, they began wondering about those other fuzzy patches scattered across the night sky. These nebulae, as they were called, came in different varieties. Some, like the famous Orion Nebula, were clearly gas clouds within our own galaxy, stellar nurseries where new stars were being born from collapsing hydrogen and dust. But others looked different through improving telescopes. They had distinct spiral shapes, bright central cores, graceful arms that seemed to curve outward into space. Some astronomers suspected these might be other galaxies, other Milky Ways existing at unimaginable distances beyond our own. The idea was almost too radical to accept. This debate raged for decades in the early 1900s. Were these spiral nebulae part of our galaxy, or were they separate star systems entirely? The question wasn't just about astronomy, it was about the fundamental nature of the universe itself. If these were other galaxies, it meant the cosmos was far larger and more populated than anyone had dared imagine. The answer came from studying a special type of star called a Cepheid variable. These stars pulse with a regular rhythm, growing brighter and dimmer in predictable cycles. Crucially, the speed of this pulsing is directly related to how bright the star actually is. By comparing how bright these stars appear from Earth with how bright they should be intrinsically, astronomers can calculate exactly how far away they are. When Edwin Hubble found Cepheid variables in the Andromeda Nebula in 1924, his measurements revealed something extraordinary. These stars were millions of light years away, far beyond the edge of our own galaxy. Andromeda wasn't a nebula at all. It was another galaxy, containing hundreds of billions of stars, just like the Milky Way. This discovery transformed our understanding of cosmic architecture overnight. The universe wasn't one galaxy, with some fuzzy clouds scattered around it. It was a vast expanse filled with countless island universes, each containing more stars than there are grains of sand on all Earth's beaches combined. Understanding that galaxies exist beyond our own Milky Way changed everything about how we see our place in the cosmos. Space suddenly became much larger, much more mysterious than anyone had imagined. Each galaxy holds billions of stars, billions of worlds, maybe even billions of other beings who look up at their own night skies and wonder what's out there. The universe operates on principles that seem almost impossible to grasp. Our sun takes roughly 230 million years to complete just one orbit around the center of our galaxy. Think about that for a moment. Every human civilization, every dinosaur, every ancient forest that ever existed, all of it happened during less than one complete trip around our galactic neighborhood. Galaxies come in different shapes, each telling its own story about time and physics. Some look like elegant pinwheels, spinning slowly in the darkness with arms that spiral outward from their centers. Others appear as smooth ellipses, like cosmic footballs filled with older, dimmer stars that have been burning for billions of years. Then there are the irregular ones, chaotic and distorted, shaped by cosmic collisions and the relentless pull of gravity. What's fascinating is how these massive structures follow the same physical laws that govern everything else. Gravity holds their stars together, keeps them moving in vast orbital patterns. The speeds involved are enormous, but the distances are even more enormous, so everything appears to move slowly from our perspective. Between the stars, Space isn't empty at all. Gas clouds drift through the galactic arms, slowly collapsing under their own weight to form new stars and planets. When massive stars explode in supernovae, they scatter heavy elements throughout space, providing the raw materials for future generations of worlds. It's like a cosmic recycling system that's been running for billions of years. Black holes sit quietly at the hearts of galaxies, including our own, influencing the motion of stars around them. Creation and destruction happen side by side in this ongoing balance, this celestial ecosystem that operates on timescales we can barely comprehend. The distances between galaxies are so vast, they challenge our ability to understand them. Our nearest large galactic neighbor, Andromeda, sits more than 2 million light-years away. Even if you could send a message at the speed of light, it wouldn't arrive there until long after humanity is changed beyond recognition. Yet despite these incredible distances, gravity still connects galaxies to each other. They move toward one another, around one another, forming groups and clusters. Our Milky Way belongs to what astronomers call the local group, a small collection of about 50 galaxies bound together by their shared gravitational influence. When you zoom out even further, the universe starts to look like a vast web. Galaxies stretch along invisible threads of dark matter, with enormous voids in between. It's humbling to realize that each distant galaxy, no matter how faint it appears, is actually a place. Not just a dot of light, but a complete world with its own history, its own rhythm, its own collection of billions of stars and planets. Some of these distant galaxies might contain civilizations, others might be entirely quiet, filled only with light and cosmic dust. If we could somehow travel among them, we'd see endless variations, galaxies colliding, merging, spinning apart, some shaped like whirlpools, others like cigars, some like uneven clouds of light. The universe never stays still. Galaxies are born, evolve, and eventually fade, just like living things, though on timescales so long that to us, they appear eternal. They begin as tiny irregularities in the density of matter, shortly after the Big Bang. Over billions of years, those small variations grow under gravity's influence, drawing in gas and dark matter, forming the first stars. Our own Milky Way was shaped by mergers with smaller galaxies over cosmic time. Even now, faint streams of stars in the halo around us are remnants of those ancient collisions. The galaxy you live in is actually a collection of histories woven together by gravity. Counting galaxies requires patience and technology far beyond what human senses can manage. Astronomers take deep images of small sections of the sky, using telescopes that can detect incredibly faint light. Each image might reveal thousands of galaxies. From there, they calculate how many such sections would cover the entire sky. The numbers grow quickly, hundreds of billions, maybe trillions, because many galaxies are too faint to detect even with our best instruments. The true total might be much higher. The universe doesn't stop where our vision ends. It continues in silence beyond the reach of light that hasn't arrived yet. These numbers are so large they almost stop meaning anything, but what they really describe is abundance. The universe didn't create just a few galaxies, it created an overwhelming multitude. Each one represents a different experiment in structure and time. Some are ancient, their stars dim and red, remnants from the early universe. Others are young, bright, and blue, filled with star-forming regions that glow like cosmic embers. Galaxies also help us understand how the universe itself is changing. Their light reveals cosmic expansion, how space itself stretches over time. The farther away a galaxy is, the faster it seems to be moving away from us. Not because it's actually moving through space, but because space itself is expanding between us. This discovery revealed that the universe isn't static. It's growing, evolving, carrying its galaxies along for the ride. Every distant galaxy serves as a witness to the changing fabric of reality itself. When you look up at the night sky, you're seeing only the closest layer of this vast structure. The galaxies beyond stretch in all directions, forming a three-dimensional ocean of light. If our eyes could see across all wavelengths, infrared, ultraviolet, radio waves, and beyond. The sky would glow with the faint presence of countless galaxies overlapping. The darkness of space isn't truly dark. It's filled with the accumulated glow of distant starlight, too dim for human eyes, but still there, like a quiet chorus humming at the edge of perception. Sometimes it helps to think of galaxies not as things, but as processes. They represent the ongoing dance of gravity, gas, and time. Stars are born, live, and die within them. Dust clouds collapse, planets form, radiation escapes into space. Over billions of years, these cycles create structure, complexity, and beauty. A galaxy isn't a static object, but a living system in cosmic terms. When we talk about how many galaxies exist, we're not counting fixed entities. We're counting living histories, each one an ongoing narrative, written in light. The next time you look up and see a faint patch of light that doesn't twinkle like a star, consider that it might be another galaxy. Some, like Andromeda, are visible even without a telescope on a clear night. What you're seeing is the combined glow of 1 trillion stars, their light blended into a single soft haze by distance. It's a direct view of another universe of worlds. Somewhere in that vast collection of light, there may be someone or something looking back in our direction, wondering if they too are alone in their corner of the cosmos, or if the night sky above them holds others like themselves. Looking up at the stars tonight, you're seeing something extraordinary without even realizing it. Each point of light belongs to one massive structure, our galactic home. We call it the Milky Way, but we've never actually seen what it looks like from the outside. Picture trying to understand the shape of a forest while you're standing in the middle of it. That's exactly our situation. We're embedded inside this cosmic structure, surrounded by its dust and light, making it impossible to step back and see the whole picture. Yet somehow, through centuries of careful detective work, we've pieced together what our galaxy actually is. The Milky Way contains roughly 200 billion stars, give or take a few tens of billions. That number is so vast it becomes almost meaningless, until you consider that each one of those stars could have planets, could have stories, could have been shining for billions of years before Earth even existed. Our galaxy stretches about 100,000 light-years from edge to edge. To put that in perspective, light from one side takes 100,000 years to reach the other side. The same light that left the far edge when early humans first discovered fire is just now arriving at the opposite end. At the center of this cosmic wheel sits something both fascinating and terrifying, a supermassive black hole called Sagittarius A. This monster weighs in at about 4 million times the mass of our Sun. Stars near it move so fast they complete entire orbits in just a few years, whipping around at speeds that would make our heads spin. The galaxy has this beautiful spiral structure, like a cosmic pinwheel frozen in slow motion. 2 main arms curl outward from the center, the Perseus arm and the Scutum Centaurus arm. These aren't solid structures though. They're more like traffic jams in space, regions where stars and gas pile up as they orbit. We live in a smaller arm called the Orion Spur, about 27,000 light-years from all that central chaos. It's actually a pretty quiet neighborhood, cosmically speaking. Far enough from the galactic center to avoid the dangerous radiation and gravitational mayhem that would make life much more difficult. Our entire solar system is racing through space at nearly 500,000 miles per hour, carried along by the galaxy's rotation. Even at that incredible speed, it takes us over 200 million years to complete one orbit around the galactic center. Since dinosaurs first appeared, we've only made about one trip around our cosmic home. Think about that for a moment. Every civilization that has ever existed, every empire that has risen and fallen, every human who has ever lived, all of it has happened during just a tiny fraction of one galactic year. We're passengers on a cosmic merry-go-round that moves so slowly we can't even feel it turning. The spiral arms of our galaxy are like stellar nurseries, filled with the raw materials for making new stars. Vast clouds of hydrogen and helium drift through these regions, slowly cooling and collapsing under their own gravity. When they reach a critical point, nuclear fusion ignites, and a new star is born. These stellar births happened constantly throughout the Milky Way. Every day, somewhere in our galaxy, new stars light up for the first time. Every day, old stars reach the end of their lives and explode, scattering heavy elements into space. It's a cosmic recycling program that's been running for billions of years. The iron flowing through your bloodstream right now was forged inside a star that exploded long before our sun existed. The calcium in your teeth, the oxygen you're breathing, even the carbon that forms the backbone of your DNA, all of it was created in the nuclear furnaces of dying stars and scattered into space by their final explosive moments. You are, quite literally, made of star stuff. Your body contains elements that have been cycling through the galaxy for billions of years, passing from star to star, from planet to planet, and now temporarily organized into the complex pattern that is you. The Milky Way isn't just sitting still in space either. Our entire galaxy is moving through the universe at over 1 million miles per hour, heading toward a collision with our nearest large neighbor, the Andromeda Galaxy. Don't worry though, this cosmic fender bender won't happen for another 4.5 billion years. When that collision finally occurs, it won't be the destructive crash you might imagine. Galaxies are mostly empty space, so the stars will likely pass right through each other without touching. Instead, the two galaxies will dance around each other for millions of years, their spiral arms stretching and distorting before eventually settling into a single larger galaxy. Future astronomers, if any exist, will call this merged galaxy Milkomeda. The night sky will be dramatically different then, filled with the light from Andromeda's stars. But for any life forms watching from Earth, assuming our planet still exists, it will be a beautiful slow-motion light show, playing out over cosmic time. Most of what makes up the Milky Way remains completely invisible to us. About 85% of the galaxy's mass consists of something called dark matter. We can't see it, can't touch it, can't detect it directly. We only know it's there because of how it affects the motion of stars and gas clouds. Without dark matter's gravitational influence, the outer regions of our galaxy would be spinning too fast to hold together. The stars should fly off into space, but they don't. Something invisible is keeping them in line, providing the gravitational glue that holds the whole structure together. Mapping our galaxy from the inside requires incredible cleverness. Dust clouds block our view of distant stars, especially when we try to look toward the galactic center. Astronomers have learned to use different types of light to peer through this cosmic fog. Radio waves can penetrate dust that stops visible light cold. Infrared radiation reveals warm objects hidden behind dark clouds. Each wavelength of light tells a different part of the story. Radio waves show us cold gas drifting between the stars. Infrared light reveals the warm glow of dust heated by nearby stars. X-rays highlight the violent regions around black holes and neutron stars. By combining all these different views, we build up a complete picture of our galactic home. The center of our galaxy is a particularly wild place. Stars there are packed together millions of times more densely than in our solar neighborhood. Some orbit the central black hole so closely that they experience time dilation effects, their clocks running slightly slower than ours due to the intense gravitational field. Occasionally, the supermassive black hole at our galaxy's heart feeds on nearby gas and dust, creating brilliant flares of radiation. These feeding events can outshine entire regions of stars, sending waves of energy rippling outward through the galaxy. Fortunately for us, we're far enough away that these cosmic fireworks pose no threat. The halo surrounding our galaxy contains some of the oldest stars in the universe. These ancient suns formed when the Milky Way was young, before it had settled into its current spiral structure. They orbit in random directions, following paths that remember the chaotic early days of galactic formation. Globular clusters, dense spheres containing hundreds of thousands of old stars, also inhabit this halo region. These clusters are like cosmic time capsules, preserving information about conditions in the early universe. Some of them are nearly as old as the universe itself, over 13 billion years old. Between the stars, space isn't empty. The galaxy is filled with an incredibly thin gas, only a few atoms per cubic centimeter. It sounds like nothing, but spread across the vast distances between stars, this material has significant mass. It's constantly flowing and churning, driven by stellar winds and supernova explosions. Magnetic fields thread through the galaxy like invisible highways, guiding the motion of charged particles and influencing how stars form. These fields are incredibly weak by everyday standards, but across galactic distances, they become powerful enough to shape the flow of matter and energy. Cosmic rays, high-energy particles accelerated by supernova shockwaves, constantly rain down on Earth. These particles began their journeys elsewhere in the galaxy, sometimes traveling for millions of years before reaching our planet. They carry information about distant stellar explosions and the magnetic environment of interstellar space. The galaxy's spiral arms aren't permanent features. They're more like waves moving through the disk, regions where stars and gas temporarily pile up as they orbit. Over millions of years, these spiral patterns wind up and fade away, replaced by new ones. The arms we see today are different from the ones that existed when the dinosaurs lived. Star formation in our galaxy follows a rhythm tied to these spiral arms. As gas clouds enter the arms, they get compressed by gravitational forces and begin collapsing to form new stars. Young, hot stars light up the spiral arms, making them visible against the darker regions between them. The Milky Way is part of a larger structure called the Local Group, a collection of more than 50 galaxies bound together by gravity. Most of these are small, dwarf galaxies, but the group includes Andromeda and a few other significant members. The entire Local Group is itself part of an even larger structure, called the Virgo supercluster. Modern space telescopes have revolutionized our understanding of the galaxy structure. The Gaia satellite has measured the precise positions and motions of over 1 billion stars, creating the most detailed map of our galactic neighborhood ever made. This data reveals that the Milky Way's disk isn't perfectly flat. Instead, it's warped and twisted, possibly due to gravitational interactions with nearby galaxies. The galaxy's rotation presents one of the great mysteries of modern astronomy. The outer regions spin faster than they should, based on the visible matter we can see. This observation led to the discovery of dark matter, but we still don't know what this mysterious substance actually is. Chemical evolution in the Milky Way follows a fascinating pattern. The oldest stars contain almost no heavy elements because they formed when the universe was young and consisted mostly of hydrogen and helium. Each generation of stars creates heavier elements and scatters them into space when they die, gradually enriching the galaxy's chemical composition. Our solar system formed about 4.5 billion years ago from material that had already been through several cycles of stellar birth and death. The heavy elements that make rocky planets possible were cooked up inside previous generations of stars and distributed through supernova explosions. The galactic magnetic field influences much more than just particle motion. It affects how stars form, how cosmic rays propagate, and even how the galaxy interacts with its surroundings. This field is generated by the combined motion of charged particles throughout the galaxy, creating a complex, ever-changing pattern. Pulses from rotating neutron stars called pulsars act like cosmic lighthouses, sending beams of radiation sweeping across space. When these beams point toward Earth, we detect regular pulses that can be measured with incredible precision. These cosmic clocks help us study the galaxy's magnetic field and the properties of interstellar space. The space between galaxies isn't empty either. Thin streams of gas connect neighboring galaxies, and our own galaxy is slowly accreting material from these intergalactic flows. Over cosmic time, this steady feeding helps galaxies grow larger and more massive. Looking toward the constellation Sagittarius on a clear night, you're peering into the heart of our galaxy through layers of intervening dust and gas. Even though visible light can't penetrate all the way to the center, the general direction is obvious from the increased density of stars in that part of the sky. The Milky Way's influence extends far beyond its visible boundaries. Its gravitational field affects the motion of nearby galaxies, and shapes the distribution of matter in our local cosmic neighborhood. We're not isolated cosmic wanderers, but part of an interconnected web of gravitational relationships. Ancient light from the galaxy's center carries information about events that happened long before human civilization existed. When you see that faint glow stretching across the night sky, you're literally looking backward in time, seeing our galaxy as it was thousands of years ago. The patience required to study galactic astronomy is almost philosophical in nature. The timescales involved dwarf human experience so completely that understanding them requires a different way of thinking about existence itself. We live our brief lives against the backdrop of cosmic processes that unfold over billions of years. When people first gazed up at the night sky, they assumed they were seeing everything. The Milky Way, with all its stars and cloudy patches, seemed like the complete picture of existence. There was no reason to think otherwise. The darkness between the stars felt like the natural boundary of all things. But humans have this peculiar trait, this restless need to push beyond what seems obvious. We're never quite satisfied with the edges we can see. As telescopes became more sophisticated, astronomers started noticing peculiar objects scattered among the familiar stars. These weren't sharp points of light like stars. They were fuzzy, diffuse, almost cloud-like in appearance. The Latin word for clouds is nebulae, and that's what these mysterious objects came to be called. Some of them made perfect sense. They were regions within our own galaxy where new stars were being born, nurseries of gas and dust glowing with the energy of stellar formation. But others, well, others were different entirely. These strange nebulae had patterns, spirals that stretched across vast distances. They were too organized, too structured to be simple clouds of gas. The question that kept astronomers awake at night was whether these spiral formations were small, local features within the Milky Way, or something else entirely, something much more profound. By the late 1800s, this mystery had become one of the biggest puzzles in science. Some astronomers believed firmly that the Milky Way contained everything that existed. Others suspected that these faint spiral nebulae might be what they called island universes, independent collections of stars, completely separate from our own galaxy. The phrase itself, island universes, carries this almost poetic weight. If these astronomers were right, then the universe wasn't just bigger than anyone had imagined, it was unimaginably bigger. The Milky Way would suddenly become just one galaxy among countless others, like a single drop in an endless ocean. The problem was measuring distances to these faint objects. Within our own galaxy, astronomers had developed clever techniques for figuring out how far away stars were. They could study how stars changed in brightness, compare them to similar stars with known properties, but these nebulae were so faint, so distant, that traditional methods simply didn't work. Lord Rosse used massive telescopes to sketch the shapes of these objects by hand. He saw spirals, bright centers, dark lanes cutting through the light. His drawings suggested these might indeed be distant worlds of their own. The debate reached its peak in 1920 with what became known as the Great Debate, two sides of the astronomical community arguing over the fundamental nature of the universe itself. The answer came from light, as so many astronomical answers do. In the 1920s, Edwin Hubble began using the most powerful telescope of his era to photograph these spiral nebulae in extraordinary detail. He was searching for something very specific, a type of star called a Cepheid variable. These stars pulse with clockwork regularity, brightening and dimming over precise periods. The beautiful thing about Cepheids is that their pulsation period directly relates to their true brightness. Once you know how bright a Cepheid actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it must be. When Hubble found Cepheids in the Andromeda Nebula, the calculations revealed something stunning. This object wasn't within the Milky Way at all. It was over 2 million light-years away, far beyond the boundaries of our own galaxy. Andromeda wasn't a nebula within our cosmic neighborhood. It was an entire galaxy, an island universe, just as the visionaries had suspected. That single discovery transformed everything humans thought they knew about their place in existence. Overnight, The universe expanded from one galaxy to billions. Those faint spiral smudges were revealed to be vast collections of stars, gas, and dust, separated by distances that strain comprehension. Think about standing at the edge of what you believe is the only ocean in the world, and then discovering that there are countless other oceans stretching in every direction, each containing its own shores, its own mysteries. That's the magnitude of what Hubble revealed to humanity. The implications rippled through every aspect of astronomy. Scientists began cataloging these newly recognized galaxies, developing classification systems based on their shapes. Spirals like our own Milky Way, smooth ellipticals, chaotic irregulars. Some appeared young and bright, others ancient and fading. As photographic techniques improved, every direction astronomers looked revealed more galaxies. There seemed to be no center to this cosmic architecture, no edge, just an endless field of light scattered across unimaginable distances. But Hubble's discoveries led to an even more profound realization. When astronomers measured the light from distant galaxies, they noticed something unexpected. The light was shifted toward the red end of the spectrum, a phenomenon called redshift. This meant these galaxies were moving away from us. Not just a few of them, but nearly all of them, and the farther away a galaxy was, the faster it appeared to be receding. This observation revealed something extraordinary about the nature of space itself. The universe wasn't static, as scientists had assumed for centuries. It was expanding. The galaxies weren't moving through space. Space itself was stretching, carrying them apart like dots on an inflating balloon. This insight gave birth to modern cosmology, the study of the universe as a whole. Each galaxy became a marker in a vast pattern, revealing how the cosmos has evolved over billions of years. What began as curiosity about faint smudges had become the foundation for understanding the entire universe. When we look at galaxies today, we're doing something remarkable. We're looking backward through time. The light from Andromeda left that galaxy when early humans were still crafting stone tools. Light from the most distant galaxies we can observe began its journey before Earth even existed. This means the night sky isn't a snapshot of the present, it's a time machine, showing us layers of cosmic history stacked upon each other. Those ancient galaxies we detect may have changed completely by now, merged with others, or vanished entirely, but their light keeps arriving, carrying stories from an unreachable past. Modern telescopes have revealed just how vast this galactic population truly is. Deep field observations point instruments at seemingly empty patches of sky and collect light for days. The results are staggering. Regions no bigger than a grain of sand held at arm's length contain thousands of galaxies, each one a complete universe of stars. If such tiny portions of sky hold so many galaxies, then the entire observable universe must contain hundreds of billions, perhaps trillions of these cosmic islands. We've discovered that galaxies aren't randomly scattered either. They form clusters, superclusters, vast filaments and walls with enormous voids between them. The universe on its largest scales resembles a web, with galaxies strung along invisible threads of dark matter. We can't see this dark matter directly, but we can infer its presence from how galaxies move and cluster. It's the scaffolding that shapes everything we observe. There's something both humbling and comforting about these discoveries. Humbling because they reveal how small and peripheral our position truly is. The Milky Way, once thought to be everything, is now just one pattern among countless others. But there's also comfort in knowing the universe isn't empty. It's alive with structure, filled with light, filled with cosmic company, even if distant and unreachable. Somewhere in those other galaxies, stars are forming, planets are orbiting, perhaps life is emerging. The same physics, the same chemistry, operates everywhere. The Milky Way is unique, but it's not alone. What's remarkable is that all of this knowledge comes from light that barely reaches our instruments. Photons that left their sources billions of years ago still carry enough information to tell us where they came from and how they've traveled. When you see a photograph of a distant galaxy, you're seeing light that has journeyed across most of cosmic history. Our understanding continues to evolve as new telescopes push deeper into space and time. We're now seeing galaxies as they existed only a few 100 million years after the Big Bang. Some of these early galaxies are surprisingly massive and bright, challenging our theories about how quickly such structures could form. The observable universe, the part we can actually see, is limited by the speed of light and the age of the cosmos. Beyond our observational horizon lie regions whose light hasn't had time to reach us yet. Those galaxies exist, but we cannot see them. The universe we know is just a fraction of what's actually out there. This reminds us that knowledge, like light itself, travels slowly through the darkness. No matter how far we look, there's always more beyond our reach. Curiosity becomes a form of reaching outward into that darkness, trying to understand what lies beyond the edges of what we can observe. To peer beyond the Milky Way is ultimately an act of imagination, as much as science. It asks us to picture what we cannot touch, to believe that what appears empty is actually filled with light too faint for our eyes to detect. It reminds us that we live in a galaxy that once seemed like everything but now feels like a single spark among countless others drifting through the cosmic web. Looking up at the night sky, you're witnessing something extraordinary without even realizing it. Those distant points of light, the ones that seem so faint and far away, they're all part of our home galaxy, the Milky Way. But here's what's truly mind-boggling, hidden beyond what your eyes can detect. There are billions upon billions of other galaxies scattered throughout space. Their light reaches us constantly, silently, carrying messages from across unimaginable distances. We humans have this deep need to count things. It's how we make sense of the world around us. We count our steps, our heartbeats, the changing seasons. When ancient people looked up at the stars, they naturally wanted to count those too. But when astronomers started trying to count galaxies, they quickly discovered they were attempting something almost impossible. The numbers became so vast, so incomprehensibly large, that counting itself started to feel like a philosophical exercise rather than a simple mathematical task. Back in the early 20th century, when scientists first realized that other galaxies existed beyond our own, they made modest estimates. Maybe a few 100 million galaxies out there, they thought. That seemed like plenty. But as telescopes got better, those numbers kept climbing higher and higher. Every improvement in technology revealed more galaxies, hiding in what appeared to be empty darkness. The universe wasn't just big, it was absolutely teeming with these massive collections of stars. Here's the tricky part about counting galaxies, though. It's nothing like counting objects on a table in front of you. Space has depth, and when you look through a telescope, you're seeing layers upon layers of cosmic structure. Bright galaxies can hide dimmer ones behind them. Clouds of dust block entire regions from view, and distance makes everything fainter until it eventually disappears completely from sight. So astronomers developed a clever workaround. They pick small patches of sky, study them intensively, count everything they can find, then multiply those numbers to estimate what might exist across the entire visible universe. It's like examining 1 square meter of a massive field, counting all the flowers you find there, then calculating how many flowers might exist in the whole field. The math is simple, but the scale is absolutely staggering. The Hubble Space Telescope gave us our first real taste of just how deep this rabbit hole goes. In the 1990s, astronomers decided to try something audacious. They pointed Hubble at a patch of sky that looked completely empty, just blackness with no visible stars or galaxies. They left the camera shutter open for days, collecting every tiny bit of light that arrived. The result was the famous deep field image, and it changed everything. In that tiny region of sky, no bigger than a grain of sand, held at arm's length, they found thousands of galaxies, each one containing billions of stars. When you multiply those numbers across the entire sky, you start to grasp the true abundance of the universe. We're not talking about millions or even billions of galaxies anymore. We're approaching numbers like 2 trillion galaxies in the observable universe alone. But here's something even more fascinating about those deep space images. They're not just showing us how many galaxies exist, they're showing us cosmic history. Light travels at a finite speed, So when you look at distant galaxies, you're seeing them as they were long ago. Some of those faint smudges in the deep field images are showing us galaxies as they appeared when the universe was only a few 100 million years old. Their light has been traveling toward us for over 13 billion years. Think about that for a moment. You're literally looking back through time, seeing the universe when it was young and galaxies were just beginning to form. Each galaxy in those images represents a different era in cosmic history. The deeper you look into space, the further back in time you're seeing. It's like having a time machine that works through light itself. Even with all this incredible technology though, we're still missing most of the story. Hubble and telescopes like it can only see galaxies that are bright enough and close enough to detect invisible light. Many galaxies are too dim, too dusty, or too far away to show up in optical images. Others emit most of their light in infrared wavelengths that our eyes can't see. That's where newer telescopes come in. The James Webb Space Telescope was specifically designed to detect infrared light, allowing it to peer through cosmic dust and spot galaxies that were previously invisible. Early observations from Webb are already forcing astronomers to revise their estimates upward. What seemed like an enormous number of galaxies now appears to be just a fraction of what's actually out there. The current best estimate suggests around 2 trillion galaxies in the observable universe. 2 trillion, each one containing hundreds of billions of stars. When you multiply all those together, you get something like 10 to the 24th power total stars. That's 1,000,000 trillion stars. The number is so large it becomes almost meaningless to our everyday experience. And here's the humbling part. That's only counting what we can theoretically observe. The observable universe is limited by how far light has been able to travel since the Big Bang. Beyond that boundary, there's more universe that we'll never be able to see. The light from those regions simply hasn't had enough time to reach us yet, and because of cosmic expansion, it never will. So when we talk about 2 trillion galaxies, we're only talking about our local cosmic neighborhood, a bubble about 93 billion light-years across. Most galaxies aren't like our Milky Way, which is actually quite large as galaxies go. The majority are small, dim dwarf galaxies that are incredibly difficult to detect. They're like cosmic minnows, swimming in a vast dark ocean. Our own galaxy has dozens of these small companions orbiting around its edges, and we're still discovering new ones. Some are so faint they were only found in recent years, and others we know about only because of their gravitational effects on nearby matter. The expansion of the universe itself makes counting even more challenging. As space stretches, light from distant galaxies gets stretched too, shifting toward longer, redder wavelengths. This redshift makes faraway galaxies appear dimmer and eventually pushes their light beyond what our instruments can detect. There's a cosmic horizon beyond which galaxies become invisible to us, not because they're not there, but because their light has been stretched beyond recognition. What's particularly fascinating is that most of the universe's mass isn't in galaxies at all. The visible matter, the stars and planets we can see, makes up only a tiny fraction of what's out there. Most of the universe consists of dark matter and dark energy, invisible components that we can only detect through their gravitational effects. Galaxies form along vast filaments of dark matter, like decorations hanging on an invisible cosmic web. From our position inside the Milky Way, we face another challenge. Our own galaxy's dust and gas block our view in certain directions, creating what astronomers poetically call the zone of avoidance. It's like trying to count all the houses in a city while standing inside one building, with parts of your view blocked by walls and furniture. Astronomers use radio and infrared telescopes to peer through some of this obscuration, but our census of galaxies will always have gaps. There's something profound about this whole endeavor that goes beyond mere mathematics. We're creatures built to understand small, tangible things, the objects we can hold in our hands, the distances we can walk in a day. Yet here we are, trying to comprehend a universe so vast that it defeats our intuition at every turn. The numbers we calculate are always provisional, always incomplete, but they point towards something magnificent. If you could somehow see all the galaxies at once, every faint glow from every distant cluster, the night sky wouldn't look dark at all. It would be filled with light. The darkness we see exists not because space is empty, but because most of that light is too faint for our eyes to detect. In reality, the universe glows softly in every direction, bathed in the combined radiance of countless galaxies. Right now, photons from distant galaxies are passing through your body, through the walls around you, through the entire Earth. They began their journey billions of years ago in the hearts of stars you'll never see, escaped their home galaxies, and crossed the expanding cosmos to arrive here, in this moment. You're constantly bathed in this gentle rain of ancient starlight. When we count galaxies, we're really counting the sources of these cosmic whispers, trying to catalogue the places where light begins its epic journey across space and time. It's a dialogue between what we can measure and what we can imagine, between the finite capabilities of our instruments and the apparently infinite creativity of the universe. Perhaps the most beautiful aspect of this cosmic census is that it will never be complete. Every new telescope reveals more galaxies, more structure, more complexity than we expected. The universe seems generous with its wonders, always offering more to discover. Just when we think we've glimpsed a full picture, we find that we've only seen a tiny fraction of what exists. The act of counting galaxies connects us to something much larger than ourselves. Every galaxy we detect is linked to all the others through gravity, through light, through the shared history of cosmic evolution. When you contemplate how many galaxies exist, you're also contemplating your place within this vast network of matter and energy that we call the universe. And the counting continues. Somewhere beyond the faintest galaxies we can currently see, there are others still hidden, their light still traveling toward us across the cosmic dark. When it finally arrives, we'll add them to our tally, not to reach some final answer, but to continue this ancient human conversation with the cosmos. Because in the end, counting the uncountable isn't really about reaching a total, it's about maintaining our sense of wonder at the sheer abundance of creation itself. The universe has a way of keeping its secrets hidden in plain sight. When scientists first decided to point their most powerful telescope at what appeared to be absolutely nothing, they were essentially gambling with time itself. The Hubble Space Telescope, floating high above Earth's atmosphere, focused its unblinking eye on a patch of sky, so unremarkable that most people would dismiss it as empty darkness. This wasn't just any ordinary observation. The telescope stared at this seemingly barren region for days on end, collecting individual particles of light, photon by photon. Each tiny speck of light had been traveling through space for unimaginable periods, carrying stories from distant corners of the cosmos. The process required extraordinary patience, the kind that modern life rarely demands of us. What emerged from this cosmic staring contest changed everything we thought we knew about emptiness. The darkness wasn't dark at all. Thousands upon thousands of galaxies materialized in that single frame, each one glowing with the combined light of billions of stars. Some appeared as perfect spirals, others as irregular blobs of light, and still others as faint red smudges barely visible against the cosmic backdrop. The scale of this discovery hits you in waves. That tiny window of sky, smaller than what a grain of sand would cover if held at arm's length, contained more galaxies than anyone had dared to imagine. If such a minuscule fraction of the sky held thousands of these massive star systems, then the entire visible universe must be absolutely saturated with them. We're talking about hundreds of billions of galaxies, each one a complete world unto itself. Think about what this means for a moment. Every direction you could possibly look in space reveals the same incredible abundance. There's no empty space, no vacant lots in the cosmic neighborhood. The universe operates more like a bustling city than a sparse countryside, with galaxies packed into every available corner of existence. The light captured in these images carries more than just beauty, it carries time itself. The closest galaxies in the picture are relatively nearby, maybe a few 100 million light years away. But as your eye moves deeper into the image, you're literally looking further back in time. Those faintest, reddest galaxies at the very edge of detection are showing us what the universe looked like over 13 billion years ago. This creates a peculiar form of time travel. Every pixel in the image represents a different moment in cosmic history. The foreground galaxies show us the recent past, while the background ones revealed the universe when it was just a cosmic infant. It's like having a family photo that spans billions of generations, all in one frame. Scientists didn't stop with that first incredible image. They kept pushing deeper, extending exposure times from days to weeks. The Hubble Ultra Deep Field, and later the Extreme Deep Field, revealed even more distant, even more ancient galaxies. Some of these cosmic pioneers existed when the universe was still figuring out how to make its first stars. These ancient galaxies look nothing like the mature spiral systems we see nearby. They appear chaotic, irregular, almost frantic in their star formation. They're cosmic teenagers, full of energy and growing rapidly. By comparing these young galaxies with older, more mature ones, astronomers can trace the entire life story of cosmic evolution. The numbers behind these images are staggering in their own right. Each photon that reached the telescope's sensors had been traveling for billions of years without stopping, without wavering, carrying its message across the vast emptiness between galaxies. The fact that this light arrives at all seems almost miraculous when you consider the distances involved. Modern telescopes have taken this cosmic archaeology even further. The James Webb Space Telescope can see light that has been stretched so much by the universe's expansion that it no longer appears in visible colors. This infrared vision reveals galaxies that formed less than 500 million years after the Big Bang itself, when the universe was still learning how to organize matter into stars and galaxies. What's fascinating is how these early galaxies challenge our understanding. They appear more massive and numerous than theoretical models predicted. The universe seems to have been more efficient at forming stars in its youth than we gave it credit for. Each new observation forces scientists to revise their assumptions about how quickly cosmic structure could emerge from the smooth, featureless state that followed the Big Bang. The deep field images reveal something profound about cosmic democracy. No matter which direction astronomers point their telescopes, they see the same incredible abundance of galaxies. The universe doesn't play favorites. There's no special corner that gets more galaxies than others. This uniformity tells us something fundamental about our place in the cosmos. We're not at the center of anything. We're simply participants in a universe that looks the same from every possible vantage point. This realization carries a strange comfort. We're simultaneously insignificant and completely integrated into the cosmic story. Every atom in our bodies was forged in the nuclear furnaces of stars, some of which might be visible in these deep field images. We're not separate from this cosmic abundance. We're products of it. The process of creating these images represents human curiosity at its finest. Generations of scientists, engineers, and dreamers contributed to the technology that made these observations possible. Every component, from the mirrors to the sensors to the mathematical algorithms that process the data, represent countless hours of human ingenuity and persistence. But perhaps the most remarkable aspect of the deep field is what it reveals about the nature of patience itself. In our instant gratification world, these images required a different kind of commitment. The willingness to point a telescope at apparent nothingness and wait for the universe to reveal its secrets. This patience was rewarded with one of the most profound discoveries in human history. The light in these images connects us directly to cosmic history. When you look at the deep field, you're seeing light that began its journey when the universe was a completely different place. Some of these photons started traveling before our solar system even existed. They've crossed nearly the entire observable universe to reach our detectors, carrying news from a time when galaxies were just beginning to form. Each galaxy in the image represents billions of individual stars and potentially trillions of planets. Some of those worlds might harbor oceans, atmospheres, even life. The statistical probability suggests that among all those countless worlds, we're probably not alone. Somewhere in that field of galaxies, other beings might be conducting their own observations, creating their own deep field images, wondering about their place in this vast cosmic community. The deep field also demonstrates the universe's remarkable efficiency at preserving information. Light from the most distant galaxies has traveled for over 13 billion years without losing its essential message. Despite crossing vast regions of apparently empty space, Despite the universe's expansion stretching its wavelength, the light arrives intact, ready to tell its story to anyone patient enough to listen. Modern analysis of these images goes far beyond simple observation. Each galaxy becomes a data point in elaborate calculations about cosmic evolution, dark matter distribution, and the rate of star formation throughout cosmic history. Scientists can measure not just what these galaxies look like, but how fast they're moving, what they're made of, and how they've changed over time. The deep field images continue to influence how we think about infinity and endlessness. While the universe might not be mathematically infinite, these images give us the closest thing to that experience. Your eye can wander from galaxy to galaxy without ever finding an edge or boundary. There's always another faint smudge, another distant system, another chapter in the cosmic story. This creates a unique form of meditation. The deep field invites contemplation in a way that few scientific images can match. It's simultaneously humbling and inspiring, showing us both our cosmic insignificance and our remarkable ability to understand our place in this vast system. We've managed to capture infinity in a photograph, to hold the entire visible universe in the span of our attention. The legacy of the deep field extends beyond astronomy into philosophy and art. It changes how we see our own night sky, transforming apparent emptiness into hidden abundance. Every dark patch between visible stars now carries the promise of thousands of unseen galaxies, each one a complete universe of possibilities. Perhaps most importantly, the deep field represents hope for continued discovery. It proves that the universe still holds surprises, that patient observation can reveal wonders we never suspected. As technology improves and new telescopes come online, we'll undoubtedly see even deeper, even further back in time, uncovering new chapters in the cosmic story. The light captured in these images will outlast the civilizations that recorded it. Long after our current technology becomes obsolete, the information preserved in the deep field will continue telling the story of cosmic evolution. It's a gift from the universe to any intelligence capable of receiving it. A demonstration that the cosmos is not only stranger than we imagine, but more wonderful than we ever dared to hope. The act of measuring what exists beyond our reach begins with something as fragile as light itself. Photons that have journeyed for billions of years arrive at our telescopes, one by one, carrying stories from places we'll never visit. Each particle of light becomes a messenger. But reading its message requires us to trust in physics, in mathematics, in the long chain of reasoning that connects a glowing dot on a screen to a galaxy spinning in the void. When astronomers count galaxies, they're not collecting objects like coins in a jar. They're gathering light, ancient and thin, that has crossed unimaginable distances. This light gets transformed into electronic signals, then into numbers, then into maps that reveal the architecture of existence. It's like trying to understand an entire forest by studying only the shadows its trees cast on the ground. Those beautiful deep field images we see, bursting with color and form, represent an extraordinary feat of detection. A distant galaxy might send us only a handful of photons over the course of hours, or even days. Each photon hits a detector and becomes an electronic pulse. Computers then process these signals, filtering out noise, correcting for the distortions caused by our atmosphere and our instruments. Software algorithms scan these processed images, looking for tiny variations in brightness that might indicate a galaxy. Each candidate gets compared against models to determine whether it's really a galaxy, just a nearby star, or perhaps an artifact created by the telescope itself. Only after this lengthy process does a single point of light earn its place in our cosmic census. What's remarkable is how much information these faint traces can reveal. A galaxy that appears as nothing more than a blur might be billions of light years away, yet its spectrum, the detailed breakdown of its light by wavelength, tells us about its distance, its motion, even what elements it contains. Light that has traveled for 13 billion years still carries the chemical signatures of the stars that created it. Hydrogen, helium, traces of oxygen and carbon, all leave their fingerprints in the light. By studying how this light gets stretched during its journey, scientists can measure how fast the galaxy is moving away from us. The farther the light has traveled, the more it gets redshifted, its wavelength stretched by the expansion of space itself. This cosmic redshift becomes our measuring stick, the ruler we use to gauge distances across the universe. To transform these distance measurements into actual counts of galaxies, astronomers conduct systematic surveys of the sky. These surveys use wide-field telescopes that can capture enormous sections of the heavens in a single exposure. Each survey generates terabytes of data, far too much for any human to examine directly. Algorithms must sift through it all, cataloging billions of points of light. Different surveys focus on different wavelengths of light. Some capture visible light, others work in infrared or radio waves. Each wavelength reveals a different population of galaxies. Visible light shows us young, bright galaxies actively forming stars. Infrared penetrates dust to reveal older, more obscured galaxies. Radio waves can detect massive structures where gas is still gathering to form new stars. Combined, these multi-wavelength observations give us a more complete census, like taking inventory with several different types of eyes. But even the most thorough survey can only sample a portion of what's out there. We can't observe the entire universe directly, not even the whole sky from our vantage point on Earth. So astronomers use what they can see to infer what they cannot. They measure how many galaxies exist in a given volume of space, then multiply that density by the estimated size of the observable universe. It sounds simple, but the execution proves anything but straightforward. Galaxies aren't distributed uniformly throughout space. Some regions teem with clusters and filaments of galaxies, while others contain vast voids that are nearly empty. To estimate accurately, scientists must understand this cosmic structure, how galaxies are arranged across different scales. They create computer simulations that recreate the universe from its earliest moments, starting with tiny fluctuations in matter density shortly after the Big Bang. These simulations follow gravity's influence over billions of years, showing how matter clumps together, how dark matter forms scaffolding, and how gas condenses into the first stars and galaxies. By comparing these simulated universes to actual observations, astronomers can refine their estimates. If the number and distribution of galaxies in a model matches what we observe, the model is probably close to reality. If not, they adjust the physics, tweaking parameters like the properties of dark matter, the rate of cosmic expansion, or the effects of stellar feedback on galaxy formation. It's an ongoing conversation between theory and observation that never really reaches a final conclusion. Every new deep field image, every survey, every advanced telescope adds another layer of detail, another constraint on our models. Gradually, the invisible becomes visible, the unreachable becomes measurable. There's something quietly profound about how this process works. The tools we use to study the universe are built from the same matter the universe is using to study itself. Through us, metal mined from Earth becomes a mirror that catches light from galaxies older than our planet. Silicon chips process signals from stars that formed long before our solar system existed. We're using atoms forged in ancient stellar furnaces to understand those very stars. This makes counting galaxies more than just observation, it's participation. We become part of matter learning about itself through patience and reflection. To count what we cannot physically touch requires us to expand our definition of seeing itself. Human eyes evolved to handle only a narrow slice of the electromagnetic spectrum, a small window in the vast range of wavelengths that fill the universe. But galaxies radiate across this entire spectrum, from radio waves the size of buildings to gamma rays smaller than atoms. To capture their complete story, we need instruments tuned to each wavelength. Radio telescopes listen to the long, low-frequency whispers of hydrogen gas. Infrared telescopes peer through cosmic dust to reveal hidden star-forming regions. X-ray observatories detect the violent hearts of galaxies, where supermassive black holes consume matter and emit powerful radiation. Each type of telescope adds another voice to the cosmic symphony. Counting galaxies isn't just tallying points of light, it's listening to the full spectrum of existence across every wavelength nature provides. Consider how astronomers identify galaxies that remain invisible to optical telescopes. These so-called dark galaxies aren't dark because they contain only dark matter, but because they produce little or no starlight. They might consist mainly of gas clouds, or their stars might be completely hidden by thick dust. Detecting them requires radio observations tuned to the hydrogen line, a faint signal emitted by neutral hydrogen atoms. By scanning the sky for this specific frequency, scientists can map where gas accumulates, even when no visible light escapes. These hidden galaxies must be included in our count. They're part of the unseen majority that fills the cosmic inventory. Without accounting for them, our picture of the universe would remain fundamentally incomplete. Distance presents another major challenge. Light from nearby galaxies reaches us relatively unchanged, but light from distant ones arrives redshifted, dimmed, and stretched by cosmic expansion. To interpret this ancient light properly, astronomers must correct for all the effects of an expanding universe. The farther away a galaxy sits, the more its light gets shifted toward longer wavelengths, and the more uncertain its exact distance becomes. Measurements must account for the rate of universal spacetime, and how gravity warps spacetime, and how the distribution of matter affects light's path through the cosmos. The mathematics behind these corrections grows quite complex, but the underlying principle remains simple. Our universe is dynamic, constantly changing, and the light we observe carries that motion encoded within every photon. Each particle of light represents not just a point in space, but a record of motion, of change, of time itself, stretching as space expands. Counting galaxies also forces us to confront our own perspective. We're counting from within one galaxy, the Milky Way, looking outward through our local environment. Our position defines what we can observe. The disk of our own galaxy blocks our view in certain directions, and our instruments have fundamental limits. What we call the observable universe is bounded not by physical walls, but by time itself, by the maximum distance light has had time to travel since the universe began. Beyond that horizon, galaxies certainly exist, but their light simply hasn't had enough time to reach us yet. In principle, we could imagine an infinite universe filled with infinite galaxies, but infinity cannot be counted or catalogued. So we focus on measuring the portion we can detect, knowing it represents only a fragment of the whole. What's beautiful is that even this fragment reveals patterns that seem to repeat everywhere we look. Galaxies cluster together in groups. These groups form larger superclusters, which connect into vast filaments stretching across hundreds of millions of light years. The arrangement appears random at first glance, but when you zoom out far enough, a hidden order emerges. On the largest scales, the universe looks roughly the same in every direction we examine. This creates a self-similar pattern of cosmic structure. The same physical laws that shape nearby galaxies also govern those at the very edge of our visibility. When we count them, we're not just cataloging objects, we're counting repetitions, echoes of the same fundamental processes unfolding across the entire observable cosmos. To understand how this works in practice, imagine a project like the Sloan Digital Sky Survey, which has mapped millions of galaxies across about a quarter of the sky. The survey telescope, operating from New Mexico, sweeps systematically through the heavens, capturing detailed spectra for each object it detects. Each spectrum acts like a unique barcode for that galaxy, encoding information about its distance, motion, and chemical composition. The result is a three-dimensional map of our local universe, not a flat photograph, but a complete volume filled with galaxies positioned in space and time. When you visualize this data, the universe reveals itself as a vast web, with filaments of galaxies stretching across billions of light years. It's not a static canvas, but a living, dynamic structure, interconnected and constantly evolving. These maps rank among the most humbling achievements in human history. They show our position within a network of truly unimaginable scale. The maps reveal that our Milky Way belongs to a small group of local galaxies, which sits at the edge of a supercluster, which itself forms just a tiny node in structures that extend as far as our instruments can measure. This is what counting galaxies really means, not just accumulating numbers, but understanding how those numbers fit into the grand pattern of cosmic architecture. Even with all this observational data, significant uncertainty remains. The faintest, most distant galaxies often slip through our detection methods, hidden by distance, dust, or simple faintness. To estimate their numbers, astronomers rely on statistical models based on the brightness distribution of galaxies we can observe. They study how many bright galaxies exist compared to dim ones, then extrapolate that relationship to brightness levels we cannot yet detect. It's like hearing the faint echo of a distant sound and trying to guess how long that sound continues beyond the limits of hearing. These extrapolations suggest that most galaxies in the universe are actually faint, small, and easily overlooked. They're the cosmic equivalent of background noise, yet together they outnumber the bright, spectacular galaxies by enormous margins. The universe, it seems, consists mostly of the faint and the forgotten. When we attempt to count what we cannot physically touch, we inevitably confront the limits of both human senses and our most sophisticated machines. The deeper we peer into space, the more the genuine signals fade into instrumental noise. At some point, the few photons arriving from the most distant galaxies become nearly indistinguishable from the random electronic fluctuations of our detectors themselves. Separating real astronomical light from electronic noise becomes as much art as science. Teams of researchers carefully check and recheck every detection, comparing observations against theoretical expectations, verifying that what they observe represents genuine cosmic light rather than instrumental artifacts. Each confirmed galaxy becomes a small victory, not just over the challenge of distance, but over entropy itself, over the universe's natural tendency to blur fine details into uniformity. All of this work, the surveys, the simulations, the careful calibrations, exists because we fundamentally cannot travel to these distant places. We cannot reach out and physically handle a galaxy, cannot collect samples from it, cannot test its stars in earthbound laboratories. All we possess is light, but light proves sufficient. It carries within itself the complete memory of its origin, the full story of its journey across space and time. When astronomers analyze that light, they are touching something absolutely real, just in a profoundly different way than we normally understand touching. The photons entering a telescope tonight may have begun their journey before Earth had even formed. They have traveled across expanding space, through clouds of intergalactic dust, past countless other galaxies, finally ending their epic voyage in a detector built by human hands. This is what it truly means to count what we cannot touch, to translate the physically unreachable into something knowable and measurable, one precious photon at a time. Perhaps that represents the quiet magic underlying this entire endeavor. The universe doesn't surrender its secrets easily, but neither does it hide them with any malicious intent. The information is simply there, waiting patiently, written in the language of light across every wavelength. The instruments we have constructed represent our method of listening to this cosmic conversation. Each new observation adds another brushstroke to a grand portrait of existence that we may never complete, but we don't actually need to finish it. The act of creation, of discovery, of careful measurement proves sufficient in itself. The counting becomes not an attempt to capture everything, but a way to participate in the vast pattern, to acknowledge that we too belong to this cosmic structure we're working so diligently to understand. Looking up at the night sky, you're witnessing something that defies the very limits of human understanding. Those pinpricks of light you see, they're just the beginning. Beyond them, in every direction, countless galaxies drift through the cosmic dark, each one containing billions of stars. The word billion loses all meaning when you try to apply it to the cosmos. We say it casually, billions of galaxies, but a billion is 1,000 million. Each galaxy holds billions of stars. The total number of stars in the observable universe exceeds every grain of sand on every beach on Earth. That comparison gets repeated often, maybe because it makes the impossible seem almost manageable, but it doesn't really capture the truth. Sand grains are things you can touch, count individually if you had the patience. Stars and galaxies exist on a completely different scale. They're not scattered objects, they're part of a structure so vast and interconnected that no human mind can truly hold it all at once. Astronomers have a phrase they use when the numbers get too large to be meaningful. Billions upon billions. It's not really about precision. It's about acknowledging the limits of what we can comprehend. Every new telescope, every deeper survey adds to the count. What we thought was the entire universe keeps turning out to be just a small corner of something much larger. A century ago, Edwin Hubble proved that Andromeda was another galaxy, not just a nearby cloud of gas. Overnight, the known universe expanded from one galaxy to many. Since then, it's happened again and again. First hundreds of galaxies, then thousands, then millions. Modern digital surveys have catalogued billions of them, each one a separate island universe. The Sloan Digital Sky Survey mapped over 1 million galaxies in 3 dimensions. That's just a tiny fraction of what's visible. When you extrapolate those numbers to the entire observable universe, you get estimates in the hundreds of billions, maybe even a few trillion. The number becomes so large, it starts feeling philosophical. Each galaxy tells a different story. Some are massive spirals with elegant arms, where young blue stars are being born. Others are ancient and red, their star formation finished eons ago, drifting quietly through the void. Some are so faint they barely register on our most sensitive instruments. Others blaze so brightly they outshine everything around them. They cluster together in groups and chains, sometimes colliding in slow-motion ballet that takes hundreds of millions of years to complete. Sometimes they drift alone through empty regions where space stretches dark for millions of light years. Together, they form a population as diverse and dynamic as life itself. But billions upon billions isn't just about quantity, it's about variety. When the universe has enough time and matter to work with, it experiments endlessly. Every possible combination gets tried somewhere. If you could step back far enough to see the whole cosmos at once, it might look like a vast city at night. Galaxies would be the lights, scattered in every direction, some clustered in bright neighborhoods, others isolated in the suburbs. From a great distance, all those lights would blend into a smooth glow. But up close, each one has its own character, its own rhythm of birth and death, and renewal. The universe reveals structure at every scale you examine it. Galaxies gather into clusters. Clusters connect along invisible threads of dark matter, separated by enormous voids where almost nothing exists. Like cities, galaxies change over time. They grow, they fade, they merge with their neighbors. The universe isn't static, it's alive with motion and evolution, even if that evolution happens too slowly for human eyes to follow. The Milky Way races through space at hundreds of kilometers per second, so does Andromeda. So do all the others. Everything is moving, though from our perspective it all seems frozen in place. When you talk about billions of galaxies, you're talking about billions of separate histories, each one formed at its own pace, in its own way. Some assembled quickly after the Big Bang, blazing bright in the early universe. Others took their time, growing slowly from smaller pieces over billions of years. Every galaxy carries the record of its life in its light. The colors tell you about age, the brightness about size and activity. Blue light means young, hot stars are forming. Red light suggests an older, quieter population. Astronomers read these signals like historians reading ancient texts. Each galaxy is a story written in starlight, and the universe is a library containing trillions of volumes. The distances involved force you to think about time in a completely different way. Light from nearby galaxies is already millions of years old by the time it reaches us. Light from the most distant ones began its journey over 13 billion years ago, when the universe was still young. When you look at a galaxy through a telescope, you're not seeing it as it exists now, but as it was then. Each galaxy you observe exists at a different moment in cosmic history. Together, they create a timeline of the universe itself. To study billions of galaxies is to watch billions of moments from the past, like frames in an impossibly long movie about cosmic evolution. Despite all these numbers, all this activity, the universe remains strangely quiet, from our perspective. The spaces between galaxies are so enormous that even light, the fastest thing we know, takes millions of years to cross from one to another. When galaxies do collide, the process unfolds over hundreds of millions of years, far too slowly for any human to witness. What seems remarkable is that all these billions of galaxies follow the same basic rules. Gravity works the same way in distant clusters as it does in our local group. Nuclear fusion powers stars everywhere, using identical processes. The same physics that operates in the Milky Way operates in galaxies billions of light years away. This uniformity gives scientists confidence that what we learn by studying nearby objects applies to the entire cosmos. The laws of nature are truly universal. They connect the nearest star to the most distant galaxy we can detect. In that sense, billions upon billions becomes more than a statement about quantity. It becomes a statement about unity. There's something very human about our need to count the uncountable. We measure, we estimate, we make educated guesses, knowing full well that the true total will always escape us. Counting galaxies isn't really about reaching a final answer. It's about pushing against the boundaries of knowledge, about touching the infinite through understanding. When scientists use the phrase billions upon billions, they're not just describing numbers, they're describing wonder. That sense of awe that comes from realizing how much exists beyond our daily experience and how small our corner of it really is. If you could somehow travel beyond the Milky Way, out past our local group of galaxies, into the deeper universe, you would see this abundance directly. Galaxies would fill every direction, glowing softly against the cosmic night. Some would appear as thin disks, seen edge-on, others as glowing elliptical shapes. The light would layer and overlap, creating a rich tapestry of illumination. You would see massive clusters containing thousands of galaxies, all bound together by gravity. Beyond them, vast filaments of galaxies, stretching for hundreds of millions of light years. Even in the voids between these structures, faint galaxies would drift alone, scattered like dust particles in a shaft of sunlight. The phrase billions upon billions isn't exaggeration, it's literally accurate. The universe overflows with structure and light and activity. Yet for all its vastness, it still feels strangely personal. Every galaxy contains the same basic ingredients that make up your body: hydrogen, helium, carbon, oxygen, iron. The processes that power their stars once forged your atoms. When you breathe, the oxygen entering your lungs was created in ancient supernovas, possibly in galaxies that no longer exist. The same nuclear reactions that light up the cosmos once shaped the chemistry of your blood. In that sense, the billions of galaxies aren't just distant objects, they're part of you. Their history is written in your atoms. The universe repeats itself at every scale, from the largest structures down to the smallest particles. You are made of star stuff, as connected to distant galaxies as you are to the ground beneath your feet. Even with all these billions of galaxies, the observable universe has limits. The priest. We can see only about 13.8 billion years into the past, back to shortly after the Big Bang. Because space itself has been expanding during that time, the most distant galaxies we observe are now about 46 billion light years away. Beyond that boundary, we simply can't see. But the patterns probably continue. The same web of galaxies, the same clusters and filaments, stretching into distances we may never reach. Billions upon billions becomes a kind of mantra, acknowledging that there's always more beyond any horizon we can define. Every new generation of telescopes pushes that horizon a little further back. The James Webb Space Telescope, with its ability to see in infrared light, has already revealed galaxies that formed just a few 100 million years after the Big Bang. Some of them appear surprisingly bright and massive, suggesting that galaxy formation happened faster in the early universe than anyone expected. If those observations are correct, then the total number of galaxies in the young universe was even higher than current estimates. Many of those early galaxies have since merged or faded away, reducing the count visible today. The cosmos began crowded and bright, then expanded and thinned, leaving vast empty regions between the survivors. Counting galaxies becomes a way of tracking how structure evolves across cosmic time. Scientists build statistical models called luminosity functions, showing how many galaxies exist at each level of brightness. By analyzing these distributions, they can estimate totals for different epochs in cosmic history. The results tell a story of gradual change. Early in cosmic history, small, faint galaxies dominated the universe. Over billions of years, gravity pulled them together into larger structures. The total number decreased, but the average size increased. The universe trades quantity for complexity, simplicity for elaboration. It's a process that mirrors evolution in other contexts, though on timescales that dwarf any biological change. Cosmic evolution operates through merger and accretion, building larger structures from smaller ones over billions of years. Even with all our data and statistical models, the complete count remains beyond reach. Some galaxies are too faint for their light to ever reach us. Others hide behind dust lanes in our own galaxy, invisible at optical wavelengths. Still, others exist beyond the observable horizon, their light racing away faster than space itself expands. Billions upon billions doesn't represent a ceiling. It represents a window into something larger than we can fully grasp. What we observe is only a fraction of what exists, and every discovery leads to greater wonder rather than completion. When scientists discuss these cosmic numbers, their language often becomes almost reverent. The magnitude leaves little room for casual description. The universe isn't something to be conquered or fully understood. It's something to be experienced, observed, participated in. The galaxies aren't just distant curiosities. They're expressions of the same fundamental forces that created us. Counting them becomes an act of recognition, acknowledging that we exist in a cosmos that overflows with creative possibility. Every patch of apparently empty sky actually contains hidden galaxies too distant and faint for naked eyes to detect. They fill the universe like a three-dimensional web, their light still traveling, still crossing the void, still adding to the total luminosity of what exists. When you stand outside on a clear night, you're seeing only the thinnest surface layer of an ocean that has no bottom. The darkness between visible stars isn't empty, it's full of distant light, layer upon layer of it. Stretching back to the very beginning of time, billions upon billions isn't meant to overwhelm or intimidate, it's meant to put things in perspective. Not just the scale of the universe, but the scale of human achievement in understanding it. The fact that we can estimate such numbers at all represents something extraordinary. The cosmos didn't arrange itself for easy comprehension. Yet through careful observation and mathematical reasoning, we've managed to glimpse its basic architecture. We've counted enough to know that complete counting is impossible. That's actually a kind of victory, knowing there will always be more to discover. The numbers eventually fade into background, and what remains is the image itself. Countless islands of light scattered across space and time, each one glowing in every possible direction. They exist not just as data points in astronomical catalogues, but as parts of a larger whole that includes you. The same physical processes that assembled them also assembled you. The same light that illuminates them reaches your eyes. Billions upon billions of galaxies, billions upon billions of stars, and somehow, in one small corner, consciousness emerged that's capable of noticing it all. That's perhaps the real miracle here. Not the quantity, but the connection. Not the vastness, but the fact that part of the universe became aware enough to contemplate the rest of it. The counting continues with each new telescope and each deeper survey. The totals keep growing, but the sense of wonder grows even faster. Throughout all of space, countless galaxies drift completely invisible to our eyes. These hidden systems don't shine, don't glow, don't reflect any light at all. They exist in perfect darkness, made of substances that pass through the universe without leaving any visible trace. Yet somehow we know they're there. Their gravity tugs on the galaxies we can see, bending the paths of distant starlight, shaping the very bones of reality itself. It's a humbling thought, really. When you gaze up at a clear night sky, you're witnessing only the tiniest fraction of what actually exists. All those glittering stars, all those distant galaxies, sparkling in our telescopes, they represent less than 5% of everything that's out there. The remaining 95% hides in complete invisibility. About 27% consists of something called dark matter, while nearly 70% involves an even stranger phenomenon known as dark energy. Think of visible galaxies as small islands of light floating on the surface of a vast, dark ocean. Beneath those islands, invisible currents flow and swirl, determining where the islands can form, how they move, even whether they survive at all. The darkness isn't empty space, it's the foundation that makes everything else possible. This discovery came about through a simple observation that changed everything. Astronomers started measuring how fast galaxies rotate, expecting the numbers to match what Newton's laws predicted. Instead, they found something impossible. Stars at the outer edges of galaxies were moving far too quickly. The visible mass, all the stars and gas and dust they could detect, simply wasn't enough to hold these systems together. By every calculation, these galaxies should have torn themselves apart long ago, but there they were, spinning peacefully, completely intact. The only possible explanation was invisible matter, adding extra gravity to keep everything bound together. This unseen substance earned the name dark matter, and it represents one of the most profound mysteries in all of science. We can't detect dark matter directly, but we can measure its effects with remarkable precision. When light travels from distant galaxies toward Earth, it bends slightly as it passes near massive objects. This phenomenon, called gravitational lensing, works like a cosmic magnifying glass. By studying how light gets distorted along its journey, astronomers can map exactly where the hidden mass exists. The results reveal something extraordinary. Visible galaxies trace only the brightest parts of a much larger structure. Around them, between them, vast halos and filaments of dark matter stretch across billions of light years, forming an invisible web that spans the entire universe. The galaxies we see are simply the most luminous points along this hidden framework. Even our own Milky Way sits embedded within a massive halo of dark matter. This invisible envelope extends far beyond the disk of stars we call home, surrounding us completely. Right now, as you listen to these words, dark matter particles are passing through your body, through the walls around you, through the entire planet, without interacting in any way we can detect. It's like living inside an invisible building that holds everything in place. The strangest part is how essential this darkness turns out to be. If all the dark matter suddenly vanished, galaxies would simply unravel, stars would drift apart, the cosmic web would dissolve, and the universe would become a thin, formless soup of scattered particles. Light alone cannot create the large-scale structures we observe. The darkness provides the skeleton, the framework, the architectural support that makes complex structures possible. It's deeply ironic that what we call dark matter is actually what gives the universe its shape, its texture, its capacity to exist as we know it. All the beautiful, familiar light we see is essentially decoration on top of a much deeper, invisible pattern. Yet, despite understanding its effects so well, we still have no idea what dark matter actually consists of. Scientists know it's not made of ordinary atoms. It doesn't emit any kind of radiation, doesn't collide or clump the way normal matter does. The leading theories suggest it might be composed of exotic particles, things with names like weakly interacting massive particles, or axions, or perhaps something even stranger that we haven't imagined yet. Deep underground laboratories and space-based experiments are constantly searching for these mysterious particles, trying to catch the faintest hint of interaction with ordinary matter. So far, the universe has kept its secret completely. After decades of increasingly sophisticated detection attempts, we still haven't found a single direct trace of what makes up more than a quarter of everything that exists. Some galaxies consist almost entirely of this hidden substance. Astronomers have discovered systems where very few stars exist, yet the gravitational effects are enormous, These dark galaxies contain just enough visible matter to barely glow, yet they move as if filled with tremendous amounts of mass. In many cases, they're detectable only through the way they bend light from more distant objects, like ghostly shapes inferred from their gravitational shadows. Recent discoveries have made the picture even more complex. Some galaxies appear to have much less dark matter than expected, while others seem to have none at all. These exceptions challenge our models, suggesting that dark matter might distribute itself differently under various conditions or interact in subtle ways we don't yet understand. Each new observation adds another piece to an enormous puzzle, but the complete picture remains frustratingly out of reach. The truth may be far more complex than any single theory can capture. What seems certain is that the universe operates on levels that extend far beyond human senses. There's something profound about the fact that darkness, not light, represents the fundamental substance of reality. Light is rare, fragile, temporary. Stars burn out, galaxies fade, but the dark matter that shapes them endures. Without this invisible scaffolding, there would be no stars, no galaxies, no planets, no possibility for life itself. Even the light we do observe owes its existence to darkness. When we study the cosmic microwave background, that faint afterglow from the Big Bang, we see tiny fluctuations, small differences in temperature and density scattered across the early universe. Over billions of years, those minute variations grew under the influence of dark matter's gravity. It pulled ordinary matter into increasingly dense regions, forming the first galaxies along invisible threads. Without dark matter, those original fluctuations would have remained smooth and uniform. The universe would have stayed as a featureless, glowing fog, never condensing into the rich tapestry of structures we see today. Darkness, not light, gave birth to everything we know. When you stand outside on a clear night, looking up at scattered stars against the black sky, you're witnessing only the surface of something immeasurably deeper. That apparent emptiness between stars isn't nothing at all. It's filled with invisible galaxies, halos of dark matter, complex webs of gravitational structure, all existing silently, shaping what you can see. The blackness you look into is actually the presence of everything that doesn't shine. It's the substance that makes the visible universe possible. In a very real sense, when you gaze into the dark, you're looking at the foundation of existence itself. Astronomers use the term dark halo to describe these invisible envelopes surrounding every galaxy. These halos are enormous, extending far beyond the visible stars and gas. What we typically think of as a galaxy, that luminous spiral or elliptical shape, represents only the central region, a bright core within a much larger dark sphere. When galaxies collide, their invisible halos interact too, merging and stretching into long filaments. The spectacular fireworks of star formation that follow, those bright bursts and streaming tidal tails, are merely surface effects. The real dynamics happen within the invisible mass, where gravity orchestrates the entire cosmic dance. Computer simulations of the universe always begin with dark matter as the primary ingredient. The models start with an almost uniform field of mysterious particles, then let gravity work over billions of years. Gradually, the dark matter collapses into filaments and dense clumps, forming the skeleton of what astronomers call the cosmic web. Ordinary matter, the atoms that eventually form stars and planets, simply falls into these gravitational wells, collecting along the same invisible structures. Every galaxy you see in any photograph owes its existence to this unseen framework. Yet despite its fundamental importance, dark matter remains entirely theoretical. We can infer its presence, calculate its effects, predict its behavior, but we cannot isolate it, touch it, or directly observe it in any way. It remains a placeholder in our equations, a name for something undeniably real but completely ungraspable. Some scientists have proposed alternative theories, modified versions of gravity that might explain the observed galactic motions without requiring invisible mass. These ideas continue to be debated and tested, but none has yet matched the predictive power of dark matter models. For now, The simplest explanation remains that most of the universe consists of something we simply cannot see. There's a quiet beauty in that scientific humility. The galaxies hiding in darkness remind us that knowledge is always incomplete, always partial. We live surrounded by mysteries we can describe mathematically, but cannot define physically. This invisibility isn't a failure of science. It's evidence that the universe still holds layers of reality beyond our current reach. Every photon of light we collect with our telescopes comes from structures built on completely unseen foundations. Every beautiful image of a distant galaxy is actually a portrait of just the visible portion of a hidden whole. Even here in the Milky Way, dark matter's influence shapes everything around us. The stars in our galaxy's outer regions move faster than they should if only visible matter were providing gravity. Their orbital speeds tell us we're embedded within a massive halo of dark matter extending far beyond the stellar disk. Our sun moves through this halo as it orbits the galactic center, swimming through an invisible ocean of gravitational influence. In a very real sense, we live inside a dark galaxy, though we perceive only its luminous heart. The night sky we admire represents just the tip of something vastly larger, a faint glow floating atop an enormous unseen sea of matter and gravity. As telescopes become increasingly sensitive, we're beginning to detect the faintest traces of galaxies that barely shine at all. Some are so diffuse their stars spread thin across enormous volumes, giving off only whispers of light. Others hide behind veils of dust or get lost in the glare of brighter companions. These dim systems blur the boundary between visible and invisible, between light and shadow. They remind us that the universe doesn't divide neatly into what we can see and what we cannot. Instead, it forms a continuous spectrum, a gradual transition from brightness to darkness, with most of reality existing somewhere in the shadowy middle. The search for dark matter represents one of the greatest frontiers in modern science. Massive detectors deep underground wait patiently for the extraordinary rare collision between a dark particle and ordinary matter. Space missions look for subtle gravitational effects that might reveal new clues about invisible structures. Particle accelerators probe the smallest scales of reality, searching for hints of forces and particles beyond our current understanding. Each experimental effort contributes to the same fundamental quest, bringing the unseen gradually into the realm of understanding. There's a certain poetry in the idea that the darkest parts of the universe might one day illuminate our greatest discoveries about the nature of reality itself. If we can eventually understand what dark matter actually is, we'll understand how galaxies formed in the first place, how cosmic structure emerged from primordial smoothness, and perhaps even why the universe looks the way it does rather than some other way. The galaxies hiding in darkness aren't obstacles to discovery. They're the key to unlocking some of the deepest questions we can ask. Their invisibility represents not a void in our knowledge, but an invitation to look deeper, think harder, develop new ways of seeing beyond the narrow slice of the electromagnetic spectrum our eyes can detect. It's tempting to imagine the cosmos as a kind of battle between light and darkness, between the known and unknown. But the deeper truth is gentler than that. Light and darkness work as partners, not opponents. The galaxies that shine exist precisely because the dark matter holds them together. The invisible gives form to the visible, provides the stage on which the cosmic drama unfolds. Without one, the other would be meaningless, impossible, non-existent. The true beauty of the universe lies not in brightness alone, but in the intricate balance between the seen and unseen, the partnership between matter and dark matter, the dance between light and the gravitational structures that cradle it. When you look up at the night sky, try to remember that what meets your eyes is only the most superficial layer of reality. The complete universe, the full and total cosmos, extends far beyond the reach of sight. It's constructed from darkness as much as from light, shaped by invisible forces as much as by the nuclear fires burning in stellar cores. The galaxies that hide in that darkness, silent and unseen, are every bit as real as the ones that sparkle in our telescopes. They move through the same space, follow the same physical laws, contribute to the same grand story of cosmic evolution. Their existence whispers a fundamental truth about the nature of reality, that the cosmos is always deeper, stranger, more mysterious than appearances suggest. Even the darkest places, the most invisible corners of space, are filled with meaning, with substance, with gravitational significance. Somewhere out there, far beyond the reach of any light we'll ever see, entire galaxies drift through perfect darkness. Their stars are few, their glow nearly non-existent, but their gravity is profound. They bind other galaxies in gravitational embraces, bend the paths of light rays, announce their presence through subtle celestial motions that reveal their hidden influence. These dark galaxies represent the hidden half of the universe, not lost or absent, simply waiting for instruments sensitive enough and minds patient enough to find new ways of detecting their presence. Even if we never observe them directly, their gravitational fingerprints will always remain, written into the motions of everything we can see. The galaxies that hide in darkness shape the ones that shine, just as the invisible structures of reality shape every aspect of the visible world around us. They remind us that the universe's deepest truths often lie hidden in plain sight, waiting to be discovered not by looking harder at the light, but by learning to perceive the profound significance of the spaces in between. The cosmos doesn't change simply because we point our instruments toward it. Yet somehow it becomes larger each time we look. This isn't magic, it's something more subtle. Our telescopes don't create new galaxies, they reveal what was already waiting in the darkness. Every photon that reaches our detectors has been traveling for millions, sometimes billions of years, carrying information across distances we can barely comprehend. Think about how recently we discovered that other galaxies even existed. Just over a century ago, astronomers believed the Milky Way contained everything. The entire universe, as far as anyone knew, fit within the boundaries of our single galaxy. Then Edwin Hubble made measurements that changed everything. Those fuzzy patches of light weren't nearby clouds of gas and dust. They were entire galaxies, each containing billions of stars, scattered across space at unimaginable distances. This pattern repeats itself throughout the history of astronomy. Each improvement in our ability to see reveals layers of complexity that nobody expected. When Galileo first aimed a telescope at Jupiter, he discovered moons orbiting around it. This simple observation shattered the idea that everything in the heavens revolved around Earth. The universe suddenly became less human-centered, more mysterious. Radio telescopes opened up completely invisible parts of the sky. Objects that emit no visible light at all turned out to be some of the most energetic phenomena in the cosmos. Pulsars spinning hundreds of times per second, quasars pouring out more energy than entire galaxies, supermassive black holes devouring matter and shooting jets of particles across millions of light years. None of this existed in our picture of reality until we learned to detect radio waves from space. The Hubble Space Telescope gave us our first truly clear view beyond Earth's atmosphere. Ground-based telescopes, no matter how large, always had to peer through layers of turbulent air that blur and distort starlight. Hubble's sharp vision revealed that what looked like empty patches of sky were actually filled with thousands of distant galaxies. The deep field images showed us a universe far more crowded and active than anyone had imagined. But even Hubble had limitations. It could only see visible light and a small range of infrared wavelengths. The James Webb Space Telescope was designed to detect light that has been stretched by the expansion of the universe. When galaxies are extremely distant, their light gets redshifted into longer wavelengths that our eyes can't see. Webb can capture this ancient light, showing us galaxies as they existed when the universe was very young. The first images from Webb surprised astronomers. Galaxies that formed only a few 100 million years after the Big Bang looked more organized and massive than theoretical models predicted. These weren't the small, chaotic collections of stars that cosmologists expected to see in the early universe. They were large, structured systems that had somehow assembled much faster than anyone thought possible. This discovery forced scientists to reconsider their understanding of how galaxies form. Maybe dark matter played a stronger role in early cosmic evolution. Maybe star formation was more efficient in the dense conditions of the young universe. Maybe our models were missing some fundamental process. Whatever the explanation, the data showed that reality was richer and more complex than our theories suggested. Gravitational wave detectors opened up an entirely new way of observing the cosmos. These instruments can detect ripples in space-time itself, created when massive objects like black holes spiral into each other. The waves travel at the speed of light, but they carry no light at all. They're vibrations in the fabric of space, stretching and compressing the distance between objects by amounts smaller than a proton. When the first gravitational waves were detected, astronomers weren't just confirming Einstein's century-old prediction. They were adding a new sense to humanity's ability to perceive the universe. We could suddenly hear cosmic events that produce no visible light, no radio waves, no particles. The collision of two black holes creates a characteristic chirp as the objects spiral faster and faster before merging. Each detection tells us about phenomena that would otherwise remain completely invisible. Neutrino detectors buried deep underground, or in Antarctic ice, catch ghostly particles that can pass through entire planets without interacting with anything. Most neutrinos that hit Earth were created in the core of the Sun, but some come from distant supernovas or other high-energy events. These particles carry information about processes that occur in the most extreme environments in the universe, places where matter is compressed to nuclear density or heated to billions of degrees. The more senses we add, the more detailed our picture of the cosmos becomes. We're no longer limited to visible light. We can detect radio waves, microwaves, infrared radiation, X-rays, gamma rays, cosmic rays, neutrinos, and gravitational waves. Each type of signal reveals different aspects of the same phenomena. A supernova, for example, produces light across the entire electromagnetic spectrum, generates neutrinos, creates heavy elements, and may trigger gravitational waves if the core collapses into a black hole. Modern telescopes are getting larger and more sophisticated. The Very Large Telescope in Chile uses adaptive optics to cancel out atmospheric distortion, creating images sharper than those from space-based observatories. The upcoming Extremely Large Telescope, powerful enough to directly image planets around nearby stars. These ground-based instruments can be upgraded and maintained in ways that space telescopes cannot. Future space missions will survey billions of galaxies, mapping how cosmic structure evolved over time. The Nancy Grace Roman Space Telescope will create the largest panoramic view of the universe ever attempted. The Euclid mission is designed to study dark energy by measuring how the expansion of space has accelerated over cosmic history. Each survey will inevitably discover objects and phenomena that nobody anticipated. There's something profound about the fact that our observable universe has a finite boundary. Light from the most distant galaxies has been traveling toward us for over 13 billion years. Beyond a certain distance, we see the cosmic microwave background, the afterglow of the Big Bang itself. Beyond that, there's only theoretical speculation. Not because nothing exists there, but because light hasn't had enough time to reach us since the beginning of everything. This limitation is built into the structure of reality. The universe could be infinite in extent, but we can only see a finite portion of it. That boundary moves outward as time passes, revealing regions that were previously beyond our horizon. Future generations will see galaxies that are currently invisible to us, not because those galaxies don't exist now, but because their light hasn't had time to reach Earth yet. The expansion of space itself complicates this picture. Galaxies that are sufficiently far away are moving away from us faster than light, carried by the expansion of space between us. We can still see some of these galaxies because the light we're detecting was emitted when they were closer to us. But the most distant objects we can observe are receding at several times the speed of light. Their current location is much farther away than their light travel distance would suggest. When astronomers look at the newest deep field images, they often describe feeling overwhelmed by the sheer number of galaxies visible. Every patch of apparently empty sky turns out to be filled with thousands of distant objects. The void keeps revealing more structure, more complexity, more light traveling across impossible distances. Each galaxy represents billions of stars, potentially trillions of planets, countless opportunities for chemistry, and maybe even biology to create something interesting. This constant expansion of our cosmic perspective changes how we understand our place in the universe. Each generation has had to adjust to a larger, more impersonal cosmos. We learned that Earth orbits the Sun, that the Sun is an ordinary star among billions in our galaxy, that our galaxy is one of trillions scattered across space. Each step outward has been humbling, yet also strangely reassuring. The same physical laws operate everywhere. The same elements exist in distant galaxies. The same processes that created our solar system are still happening throughout the universe. Every photon that reaches our detectors is a survivor of an unimaginable journey. Some have traveled for over 13 billion years, crossing space that has expanded dramatically in the meantime. The galaxy that emitted a particular photon might now be tens of billions of light years away, even though its light has only been traveling for 13 billion years. To catch such ancient light is to witness persistence, to hold evidence of the universe's patient continuation across cosmic time. Our instruments extend our senses, but it's consciousness that learns to interpret what they reveal. When we look at a deep field image containing thousands of galaxies, we're training our minds to inhabit scales far beyond daily experience. This shift from local to cosmic thinking might be one of the most important developments in human intellectual history. We're learning to think in billions of years and light years, to imagine processes that dwarf anything we encounter in ordinary life. The universe doesn't hurry. It offers itself slowly, photon by photon, to anyone willing to build the instruments necessary to catch those signals. The light we collect today will still be traveling tomorrow. Next year, thousands of years from now, future civilizations, if they exist, will have access to information that's currently beyond our reach. They'll see farther, and their picture of reality will grow accordingly. There's a symmetry between the expansion of space and the expansion of our awareness. The cosmos grows larger as time passes, space itself stretching and carrying galaxies apart. Simultaneously, our knowledge grows outward, pushed by curiosity and enabled by better technology. These two kinds of growth mirror each other, one physical, one cognitive, creating the experience we call discovery. The galaxies don't multiply because we observe them, but our understanding of their diversity, their evolution, their role in cosmic history becomes richer. Every image adds detail to the tapestry, making it more intricate and revealing. The process remains fundamentally human, despite its technological sophistication. Curiosity drives it, the same impulse that made ancient astronomers chart constellations with naked eyes. We've simply built better tools to satisfy that curiosity, but the instinct is unchanged, to peer into darkness and wonder what's hidden there, to ask whether the next observation will reveal something unexpected. The horizon keeps moving outward, the universe keeps unfolding, and every improvement in our ability to see brings more of reality into focus. When you think about the biggest things in existence, your mind probably goes to stars, maybe galaxies, but there's something even more immense than that, something that connects everything we can see and everything we can't see too. It's called the cosmic web, and it's exactly what it sounds like, a web stretching across all of space, made of matter and emptiness, light and darkness. This web doesn't look like anything you'd expect though. It's not something you could ever see by looking up at the night sky. The pattern only shows up when astronomers spend years, decades even, carefully mapping where millions of galaxies actually are. They measure distances across billions of light years, plot everything on massive charts, and slowly, a shape emerges. Galaxies aren't scattered around randomly like you might think. They form long strings, connected threads that stretch farther than our minds can really grasp. The threads aren't made of galaxies alone though. Most of what's out there, we can't even see. Dark matter, this invisible stuff that makes up most of the universe, creates the skeleton that everything else follows. Regular matter, the kind that makes stars and planets and us, just goes where the dark matter tells it to go. Gravity pulls it all into the same patterns, the same pathways through space. Where these cosmic threads cross each other, that's where you find the biggest collections of galaxies. Massive clusters, Thousands of galaxies, all pulled together by gravity. It's like looking at a spider web covered in morning dew. Except each drop of water is an entire galaxy, and the web itself spans distances that light takes hundreds of millions of years to cross. Between the threads, there's mostly nothing. These regions are called voids, and they're some of the loneliest places you could imagine. If you were somehow floating in the middle of one, the nearest galaxy might be so far away that its light would be barely detectable. Most of the universe's volume is actually these empty spaces, while most of its matter gets concentrated along the filaments. The strangest part is how this whole structure came to be. Right after the Big Bang, everything was spread out almost perfectly evenly, just a smooth soup of matter and energy, with tiny variations in density. We're talking about differences of maybe 1 part in 100,000. But over billions of years, gravity took those microscopic differences and stretched them, amplified them, until they became the cosmic web we see today. Scientists can actually simulate this process on computers. They start with random fluctuations, let virtual gravity do its work, and watch as filaments and voids naturally emerge. The results match what we observe in the real universe with uncanny accuracy. It tells us that the same basic pattern repeats at different scales throughout the cosmos. Some of these filaments are almost incomprehensibly large. The biggest known structure, something called the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years. That's nearly 1/10 of the entire observable universe. Try to picture something that vast, that continuous, made up of thousands upon thousands of galaxies, all connected by invisible threads of dark matter. Our own galaxy sits somewhere in this web too. We're part of what astronomers call the Laniakea supercluster, a name that means immense heaven in Hawaiian. It contains over 100,000 galaxies spread across 500 million light-years. The Milky Way belongs to a small group within this larger structure, slowly drifting along one of the cosmic filaments, like a leaf on a very slow river. Everything in the universe is moving, even though it might not look that way from our perspective. Galaxies slide along the web's threads, drawn toward the massive clusters where filaments intersect. Over cosmic timescales, the whole web slowly evolves. Filaments merge together, clusters grow more massive, voids expand, and become even emptier. There's a constant tension at work here. Gravity tries to pull everything together, while the expansion of space itself stretches everything apart. The cosmic web exists in that balance, frozen in a kind of cosmic slow motion. For now, gravity is still winning, in the densest regions, building larger and larger structures. But dark energy, the mysterious force driving cosmic expansion, is gradually taking over. Billions of years from now, the web will be stretched so thin that distant galaxies will disappear from view entirely. Their light will be redshifted until it fades completely. The universe will become a lonelier place, with isolated clusters of galaxies separated by ever-growing voids. To map this structure, astronomers use surveys that catalogue millions of galaxies in 3 dimensions. One famous project mapped galaxies across billions of light-years, and when you plot all that data, the web pattern jumps right out at you. Dense knots, where clusters form, long filaments connecting them, dark empty regions between. It looks almost organic, like something alive, even though it's the largest inanimate structure we know of. The filaments aren't completely empty though. They're filled with extremely hot, extremely thin gas, heated to millions of degrees by shock waves as galaxies and clusters interact. The density is incredibly low, just a few atoms per cubic meter. But it's there. It's the universe's connective tissue, linking galaxies across unimaginable distances. What makes the cosmic web so fascinating is how it mirrors patterns we see everywhere in nature. The branching of blood vessels, the structure of neural networks, the way rivers form deltas, even how cracks spread through materials. They all follow similar mathematical principles. The universe seems to use the same basic rules to organize itself at every scale, from the smallest to the largest. This isn't just a curiosity either. The web structure tells us fundamental things about reality itself. The size and shape of filaments depend on how much dark matter exists, how dark energy behaves, what happened in the very early universe. By studying the web's geometry, cosmologists can test their theories about how everything came to be. When you look at maps of the cosmic web, you're seeing billions of years of cosmic evolution frozen in space. Every filament traces the flow of matter from the early universe to now. Every cluster marks a place where gravity won its battle against expansion. Every void shows where expansion stretched matter so thin that almost nothing remains. The web is still being mapped, still being understood. New telescopes reveal fainter filaments, hotter gas, subtler connections. Supercomputers simulate how it might look billions of years in the future. Each discovery adds another piece to the puzzle of how the universe builds itself, how it maintains its vast architecture across scales we can barely comprehend. Perhaps most remarkably, you're part of this web too. The atoms in your body were forged in stars that formed along its filaments. The gravity that shapes your daily life is the same force that sculpted its immense curves. The cosmic web isn't something distant and separate from us. It's the fundamental structure of everything, the hidden scaffolding that makes existence possible. In the end, the cosmic web represents something profound about the nature of reality. The universe isn't a collection of isolated objects floating in empty space. It's a connected whole, a vast network where everything influences everything else across distances and times that dwarf human experience. The threads that link galaxies are, in a sense, the threads that connect all of existence. The space between galaxies appears empty to our eyes, but it holds something remarkable. Dark matter weaves through these vast regions, creating an invisible scaffold that connects everything we see. This cosmic web stretches across billions of light years, linking distant galaxies like cities connected by hidden highways. What looks like nothingness actually teems with structure, with purpose, with the very foundation that allows stars and planets to exist where they do. When we think about emptiness, we usually imagine the absence of everything. But the universe challenges this simple idea at every turn. The vacuum of space itself bubbles with quantum activity, particles appearing and disappearing in fractions of seconds. Even the darkest regions between star clusters contain wisps of gas, stray photons from ancient explosions, and the gentle pull of gravity that never truly stops working. This invisible architecture shapes everything we can observe. Galaxies form where dark matter gathers most densely, like pearls strung along cosmic filaments. The Milky Way sits at one intersection of this web, surrounded by smaller companion galaxies that dance in predictable orbits. Our entire local group of galaxies moves together through space, guided by gravitational currents we cannot see but must infer from the motion of visible matter. The night sky we admire tonight represents just a snapshot in cosmic time. Those points of light that seem so permanent are actually caught in constant motion, burning through nuclear fuel at rates that vary dramatically from star to star. The brightest ones, the blue giants that dominate constellation patterns, live fast and explosive lives. They'll be gone in mere millions of years, which sounds like forever to us but barely registers as a moment in galactic time. Meanwhile, smaller stars like our Sun burn steadily for billions of years, turning hydrogen into helium in their cores with remarkable efficiency. Red dwarfs, the universe's most common stars, are even more conservative with their fuel. These dim, long-lived suns can keep shining for trillions of years, far longer than the universe has even existed so far. They represent the future of stellar evolution, the patient survivors that will outlast almost everything else. Star formation itself follows patterns that stretch across cosmic history. The universe made its first stars from pure hydrogen and helium, the only elements available after the Big Bang. These primordial giants lived briefly but crucially, forging heavier elements in their cores and scattering them through space when they died. Carbon, oxygen, silicon, iron, all the building blocks of planets and life emerged from these stellar furnaces. Each generation of stars inherits a richer mix of elements from previous generations. Our Sun formed from gas clouds already enriched by countless stellar deaths, which is why planets like Earth could form with rocky surfaces and complex chemistry. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it cycled through stellar cores at temperatures of millions of degrees. This cosmic recycling program has been running for over 13 billion years now. Gas clouds collapse to form new stars. Those stars live their lives and die, releasing their processed material back into space. Supernova explosions scatter these elements across vast distances, mixing them into the next generation of star-forming regions. It's an endless cycle of death and renewal that gradually makes the universe more complex, more interesting, more capable of supporting intricate structures. But like all cycles, this one cannot continue forever. The raw material for star formation is finite. Each new star locks away some hydrogen permanently, either burning it completely or trapping it in stellar remnants. Slowly, over hundreds of billions of years, the available gas supply dwindles. Galaxies begin to run out of fuel for making new stars. The process doesn't stop suddenly, but fades, gradually, like a fire burning down, when no one adds new wood. Star formation rates drop, and the universe begins to age visibly. The brilliant blue stars that defined spiral galaxy arms burn out without replacement. Galaxy colors shift toward red, as only the longer-lived, cooler stars remain active. The cosmic scenery grows dimmer and less dramatic with each passing eon. During this long twilight period, galaxies continue to interact and merge. Gravity operates on such vast scales that these collisions unfold over hundreds of millions of years. When two spiral galaxies merge, their distinctive arm patterns dissolve into broader, more elliptical shapes. The collision often triggers intense bursts of new star formation as gas clouds compress and heat up, creating one final fireworks show before the combined galaxy settles into a quieter middle age. Our own Milky Way faces this fate in about 4 billion years when it collides with the Andromeda Galaxy. Despite containing hundreds of billions of stars each, the galaxies are mostly empty space. Individual stars will rarely collide directly, but their orbits will be completely rearranged by the gravitational dance. The night sky visible from Earth will transform beyond recognition as new star patterns emerge from the cosmic reshuffling. This process of galactic evolution reflects something deeper about how the universe organizes itself. Gravity always tries to pull things together, creating larger and larger structures over time, but expansion works in the opposite direction, stretching space itself and pulling distant objects apart. For most of cosmic history, these two forces balanced each other, allowing complex structures to form and grow. Recently, though, expansion has begun to accelerate. This mysterious acceleration comes from dark energy, which makes up about 70% of everything in the universe, but remains poorly understood. Unlike matter or radiation, dark energy doesn't dilute as space expands. Instead, it grows stronger, gradually overwhelming gravity's ability to hold cosmic structures together. The effects of dark energy operate on the largest scales first. Galaxy clusters that might have merged billions of years from now will instead drift apart as expansion carries them beyond each other's gravitational reach. The cosmic web itself will stretch and thin until its filaments break apart completely. Eventually, even individual galaxies will become isolated islands in an ever-expanding ocean of space. From the perspective of any civilization existing in that distant era, the universe will appear almost static. The evidence for cosmic expansion, for the Big Bang, for the rich history of star formation and galactic evolution, all of it will have redshifted beyond detection. Future astronomers will see only their own galaxy surrounded by darkness, with no way to discover the broader cosmic story that preceded their existence. This creates a strange philosophical puzzle about the nature of knowledge itself. The universe contains the evidence of its own history, but that evidence becomes inaccessible over time. What we can observe and understand depends not just on our intelligence or technology, but on when we happen to exist in cosmic time. We live during a particularly rich period when galaxies are visible across vast distances and the cosmic microwave background still carries clear signatures of the universe's birth. In some sense, we're extraordinarily fortunate observers. We exist late enough for heavy elements and complex chemistry to be common, but early enough to see the universe while it's still dynamic and well lit. A civilization arising trillions of years in the future would inhabit a much lonelier cosmos, with far fewer clues about cosmic origins and evolution. Even the longest-lived stars cannot burn forever. Red dwarfs will eventually exhaust their hydrogen fuel and fade into white dwarf remnants. These incredibly dense objects about the size of Earth, but containing the mass of a star, will glow only from leftover heat. Over immense periods, they'll cool from white-hot to red to invisible black dwarfs that emit no light at all. By this point, black holes will dominate what remains of galactic centers. These gravitational monsters will continue growing by slowly consuming any matter that ventures too close. Occasionally they'll merge with other black holes, releasing tremendous bursts of gravitational waves that ripple through empty space, with no one left to detect them. But even black holes face an ultimate fate. Quantum mechanics suggests that they must slowly evaporate through a process called Hawking radiation. The effect is incredibly weak for stellar mass black holes, which would take longer than the current age of the universe to lose even a tiny fraction of their mass. But given enough time, measured in numbers so large they have no meaningful comparison, even the most massive black holes will fade away completely. The final photons from evaporating black holes will mark the end of the luminous era entirely. After that, the universe enters a phase where almost nothing happens. Particles drift through space at enormous distances from each other. Temperatures approach absolute zero. The expansion continues, but there's nothing left to expand except empty space itself. This ultimate fate seems profoundly melancholic when viewed from our current perspective. We live in an age of light, surrounded by billions of galaxies, each containing billions of stars. The idea that all of this cosmic grandeur will eventually fade into darkness challenges our sense of permanence and meaning. Yet there's something oddly comforting about the universe's long view of time. The same physical laws that will eventually extinguish the stars also created them in the first place. Nuclear fusion, gravity, thermodynamics, quantum mechanics, these fundamental forces shaped everything from the first moments after the Big Bang to the present day. They'll continue operating long after human civilization has ended, following their mathematical rules with perfect consistency. The universe doesn't experience time the way we do. It has no sense of urgency, no fear of endings, no nostalgia for brighter days. Stars form when conditions allow it, burn as long as their fuel lasts, and fade when physics demands it. Galaxies merge when their orbits intersect and drift apart, when expansion overcomes their mutual attraction. Everything unfolds according to natural processes that care nothing for our emotional responses to cosmic change. Perhaps this perspective offers its own form of wisdom. The universe teaches patience on scales that dwarf human experience. It demonstrates that change and impermanence are built into the very fabric of reality, not as flaws to be overcome but as essential features of how existence works. The temporary nature of stars and galaxies doesn't diminish their beauty or significance. If anything, it makes their current brightness more precious. When we observe distant galaxies through telescopes, we're seeing them as they existed millions or billions of years ago. When their light first began its journey toward Earth, some of those galaxies might have already faded or merged with neighbors, but their ancient light still travels toward us, carrying information across the cosmos, like messages from the past. This means our night sky contains multiple layers of cosmic time. The nearest stars show us the Milky Way as it exists now. More distant stars reveal our galaxy's structure from decades or centuries ago. Other galaxies appear as they were in the distant past, some from when the universe was much younger and more active. Looking into space always means looking backward in time, seeing the universe's history spread out across different distances. The cosmic microwave background radiation offers the most ancient view possible with current technology. This faint glow comes from about 400,000 years after the Big Bang, when the universe first became transparent to light. Before that moment, space was too hot and dense for photons to travel freely. The microwave background shows us the universe as a young, smooth, hot gas, beginning to cool and form the first atoms. Everything we observe today grew from tiny fluctuations in that early cosmos. Regions that were slightly denser than average eventually became the seeds of galaxies and galaxy clusters. Areas that were slightly less dense became the voids between them. The cosmic web we see now was already sketched out in that primordial radiation, waiting billions of years to develop into the complex structures we observe today. This connection between past and present reveals something profound about cosmic evolution. The universe has always been changing, but it changes according to patterns that persist across vast scales. The same gravitational instabilities that created the first galaxies continue operating today. The same nuclear processes that powered the earliest stars still fuel the ones we see tonight. The universe grows older and more complex, but its fundamental behavior remains remarkably consistent. Understanding this continuity helps us place our own existence in context. We're made of elements forged in stellar cores across billions of years of cosmic evolution. Our planet formed from debris left behind by previous generations of stars. The energy that powers our civilization ultimately comes from nuclear fusion in the sun, the same process that lights every star in the night sky. We're not separate from the universe looking in from the outside. We're part of it, temporary patterns of matter and energy organized into forms capable of consciousness and curiosity. When we study astronomy, we're essentially investigating our own origins and destiny on the largest possible scales. The cosmic story is also our story, told in a language of physics and chemistry that applies everywhere and always. The eventual dimming of the stars doesn't erase the significance of this cosmic flowering of complexity. For billions of years, the universe has been creating conditions that allow intricate structures to emerge. Planets, atmospheres, oceans, life, intelligence, all of these represent remarkable achievements in the ongoing process of cosmic evolution. The fact that they cannot last forever doesn't diminish their extraordinary nature. Even in the far future, when the last stars fade and the universe grows cold and dark, the information that defines every particle and interaction will persist. The mathematical relationships that govern how things behave, the quantum states that describe each bit of matter and energy, all of this structure remains encoded in the fabric of spacetime itself. The universe may lose its light, but it never loses its essential nature. When you pick up a warm cup, you're holding something that connects to every corner of existence. The ceramic was shaped by hands, but its atoms were forged in stellar furnaces billions of years ago. That simple object carries the entire history of the cosmos in its molecular structure. Your blood contains iron that came from exploding stars. The calcium strengthening your bones formed in ancient stellar cores. Every breath you take includes oxygen created when massive suns reached the end of their lives. You're not just observing the universe, you're built from its recycled materials. The same physics that governs distant galaxies also controls the steam rising from hot tea. Gravity pulls both planets into orbit and liquid toward the bottom of your cup. The electromagnetic forces binding atoms together work identically, whether those atoms form a person or a star. Heat flows from your tea to the surrounding air, following the same thermodynamic principles that drive stellar evolution. Energy always moves toward equilibrium, whether it's cooling your drink or powering nuclear fusion in distant suns. The timeline differs, but the underlying process remains identical. Scientists have discovered that the geometry describing curved spacetime around black holes also explains why liquid settles evenly in a container. The mathematics of cosmic expansion mirrors the way ripples spread across a water surface. These aren't coincidences, they're expressions of universal laws operating at different scales. Light from the most distant galaxies has traveled for billions of years to reach your eyes. That ancient radiation, carrying information from the early universe, ends its cosmic journey by creating electrical signals in your brain. You become the final destination for photons that began their trip when the cosmos was young. The neural networks processing these thoughts follow patterns similar to the large-scale structure of the universe itself. Both create webs of connection, both organize information through networks that branch and cluster. Your consciousness emerges from the same organizational principles that shape galactic filaments. Every heartbeat depends on chemical reactions powered by energy that originated in the sun's core. Photosynthesis captures sunlight, stores it in plants, and releases it again when you digest food. You're literally fueled by nuclear fusion happening 93 million miles away. The carbon atoms forming your DNA have been recycled through countless cosmic processes. They might have once been part of interstellar dust clouds, ancient planetary atmospheres, or even other living beings. Matter continuously transforms while following unchanging physical laws. When astronomers point telescopes at distant galaxies, they're using instruments built from cosmic material to study cosmic material. The aluminum in the telescope mirror, the silicon in electronic sensors, the copper in connecting wires, all formed inside dying stars. The universe examines itself, using tools made from its own substance. Quantum mechanics governs both the fusion reactions powering stars and the electron transfers, enabling your thoughts. The same uncertainty principle that determines stellar luminosity also controls the chemical bonds in your brain. Scale changes everything except the fundamental rules. The expansion of space itself can be understood through everyday analogies. Imagine dots drawn on a balloon's surface. The dots represent galaxies, and as you inflate the balloon, every dot moves away from every other dot. No single point is the center of expansion, just as no galaxy sits at the center of cosmic expansion. Time passes differently depending on gravity and motion, but these effects occur everywhere. Your head ages slightly faster than your feet because it's farther from Earth's gravitational center. The difference is unnoticeable in daily life, but GPS satellites must account for similar effects to maintain accuracy. The visible universe contains roughly the same number of stars as neurons in a human brain. Both numbers hover around 100 billion. This might be pure coincidence, but it suggests that complexity emerges at similar scales, whether you're examining consciousness or cosmos. Dark matter makes up most of the universe's mass, yet we can't see it directly. Similarly, most of your brain activity happens below conscious awareness. The visible thoughts floating through your mind represent only a small fraction of the neural processing occurring continuously in the background. Energy cannot be created or destroyed, only transformed from one form to another. The heat warming your hands once burned inside stellar cores. It converted matter to energy, traveled across space as radiation, powered plant growth through photosynthesis, and now flows through your metabolism. Nothing is ever truly lost. The elements heavier than hydrogen were created inside stars through nuclear fusion. Each generation of stars produces these materials and releases them when the star dies. This cosmic recycling program has been running for over 10 billion years, steadily enriching space with the building blocks of complexity. Your ability to contemplate infinity emerges from finite neural structures. Somehow, arrangements of ordinary atoms give rise to thoughts that can encompass concepts far larger than themselves. A brain weighing 3 pounds can hold mathematical models of structures spanning billions of light years. The light reaching your eyes right now left the sun 8 minutes ago. You're seeing the past every moment, experiencing the delayed version of reality. When you look at distant stars, you're seeing years or centuries into the past. The deeper you look into space, the further back in time you travel. Gravity shapes both the orbits of planets and the circulation of blood through your arteries. The same inverse square law that keeps Earth circling the sun also influences how fluids flow through curved vessels. Your cardiovascular system operates according to cosmic principles, scaled down to biological dimensions. The universe's age, roughly 14 billion years, seems impossible to grasp directly. But consider that the atoms in your body have existed for most of that time. They've been part of gas clouds, multiple generations of stars, possibly other planets, and now temporarily form the pattern that is you. Each breath includes atoms that have circulated through countless other organisms throughout Earth's history. You're sharing air molecules with every person who ever lived, with dinosaurs, with the first bacteria that learned to photosynthesize. The atmosphere connects all life across deep time. The weak nuclear force responsible for certain types of radioactive decay operates inside your body constantly. Carbon-14, in your tissues undergoes slow transformation, providing a natural clock that archaeologists use to date ancient materials. You carry cosmic timekeeping within your cellular structure. Temperature represents the average motion of atoms and molecules. When you feel warmth, you're sensing the kinetic energy of particles bouncing against your skin. That same molecular motion, scaled up enormously, creates the pressure that ignites nuclear fusion in stellar cores. The speed of light provides a fundamental limit that affects everything from chemical reactions to cosmic expansion. Information cannot travel faster than light, whether it's a nerve impulse in your brain or gravitational waves propagating through space. The universe operates within this universal speed limit at every level. Even in seeming emptiness, space contains energy in the form of quantum fluctuations. Virtual particles constantly appear and disappear, creating a background activity that influences cosmic evolution. The vacuum around you isn't empty, it's full of invisible potential continuously expressing itself in subtle ways. Every atom that makes up your body was forged inside a dying star, billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it came from nuclear furnaces burning in space, long before Earth even existed. When massive stars collapse, they scatter these elements across the galaxy, seeding future worlds with the ingredients for life. You're not just observing the universe, you're made from it, assembled from stellar debris that drifted through space for eons. The light reaching your eyes tonight began its journey when the universe was completely different. Some photons left their stars before our solar system formed, traveling through the expanding fabric of space, carrying information from a cosmos that no longer exists. These ancient messengers arrive here constantly, every second, delivering news from the deep past. Your retina catches them, converts them to electrical signals, and suddenly you're connected to events that happened billions of years ago. Space isn't actually empty, even though it seems like a vast void between stars. It's filled with invisible fields, virtual particles popping in and out of existence, magnetic forces, and the faintest whisper of radiation left over from the Big Bang itself. This cosmic background radiation fills every cubic inch of space, a kind of afterglow from when the universe first became transparent to light. Radio telescopes can detect this ancient heat, still warm after nearly 14 billion years. Our galaxy spins like a giant pinwheel, but so slowly that in a human lifetime, the stars barely seem to move. The Sun takes about 225 million years to complete one orbit around the galactic center. Dinosaurs lived during the last time we were in this same position. The Milky Way has made only about 20 full rotations since it formed, which means our galaxy is still relatively young in cosmic terms, still settling into its final structure. Dark matter outweighs everything we can see by about 5 to 1. Yet it interacts with ordinary matter only through gravity. Right now, particles of dark matter are streaming through your body, through the Earth, through everything, without leaving a trace. Scientists think it forms an invisible scaffolding that holds galaxies together, a hidden architecture underlying all the visible structures in space. We can map its presence by watching how it bends light from distant galaxies, creating gravitational lenses that magnify and distort the view. The universe is expanding, but not like a balloon inflating into empty space. Space itself is stretching, carrying galaxies away from each other. The farther away a galaxy is, the faster it's receding from us, which means the most distant objects we can see are racing away at nearly the speed of light. Eventually they'll cross a boundary where their light can never reach us again, disappearing beyond what astronomers call the cosmic event horizon. Black holes warp space-time so severely that time itself slows down near them. If you could watch someone fall toward a black hole, you'd see them freeze at the edge, their image growing redder and dimmer but never quite disappearing. From their perspective, they'd cross the boundary in finite time, but the universe would age infinitely around them. Some physicists think black holes might be connected by shortcuts through higher dimensions, creating bridges between distant parts of space and time. Neutron stars pack more mass than our Sun into a sphere only 12 miles across. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. These stellar corpses spin hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses. When those beams point toward Earth, we detect them as precisely timed pulses, so regular they were once mistaken for signals from alien civilizations. The observable universe contains roughly 2 trillion galaxies, each with billions or trillions of stars. Many of those stars have planets, and current estimates suggest there could be more planets than stars in the cosmos. The sheer number makes it almost certain that life exists elsewhere, perhaps in forms we can't even imagine. Some planets orbit multiple stars, experiencing complex seasons as they're heated by different colored suns throughout their years. Quantum mechanics reveals that particles can exist in multiple states simultaneously until they're observed. This isn't just a quirk of tiny things, it's fundamental to how reality works. The same principles that allow electrons to tunnel through barriers also power the nuclear fusion in stars. The uncertainty principle ensures that space can never be completely empty, always bubbling with virtual particles that borrow energy from the vacuum and pay it back almost instantly. Time passes differently depending on how fast you're moving and how deep you are in a gravitational field. Satellites orbiting Earth experience time slightly faster than we do on the surface, gaining about 38 microseconds per day. Without correcting for these relativistic effects, GPS systems would quickly become useless, accumulating errors of several miles within weeks. The cosmic web stretches across the universe like a three-dimensional spider web, with galaxies strung along filaments of dark matter separated by vast empty regions called voids. These voids can be hundreds of millions of light years across, containing almost no galaxies at all. If you lived in the middle of one, you might think the universe was empty, except for your own small cluster of stars. Red giant stars swell to enormous sizes as they near the end of their lives, some growing large enough to swallow the orbits of inner planets. When our Sun reaches this phase in about 5 billion years, it will engulf Mercury and Venus, and possibly Earth too. But long before that happens, the increased solar output will boil away our oceans and strip away our atmosphere, making the planet uninhabitable. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent events constantly bombard Earth from all directions. The atmosphere protects us from most of them, but some still reach the surface, occasionally flipping bits in computer memory or causing electronics to malfunction. Astronauts see flashes of light when cosmic rays pass through their eyes, striking the retina directly. The elements heavier than iron can only be created during the most extreme events in the universe, like neutron star collisions or certain types of supernova explosions. The gold in your jewelry, the uranium in nuclear reactors, the platinum in catalytic converters, all of it was forged in these cataclysmic mergers that make the collision of black holes seem gentle by comparison. Some theories suggest our universe might be one of countless others in a vast multiverse, each with different physical laws and constants. In most of these hypothetical universes, the conditions wouldn't allow for stars, planets, or life to form. We exist in one of the rare universes where the laws of physics permit complexity, where matter can organize itself into galaxies, worlds, and thinking beings. The cosmic microwave background radiation shows tiny fluctuations in temperature that represent the seeds of all large-scale structure in the universe. These quantum ripples, stretched to cosmic proportions by inflation, in the first fraction of a second after the Big Bang, eventually grew into the galaxies and galaxy clusters we see today. The pattern of these fluctuations encodes information about the universe's composition, age, and ultimate fate.
you.